Right off the hotel. What?
Last one just 2 minutes ago.
Uh-huh.
You were anyway on the mail. And starting the minutes document, but I want on LinkedIn to say that.
Oh, perfect. Perfect with kitties.
Yes.
You know who's the one who's going to appreciate it. One for you and probably one for Gavin.
A lot of preparation. This was the additional budget for the
To put numbers on
Yes, so that
it.
they-
You
and-
wonderfully efficient person. You.
And the first name for the people so that they know which one is theirs.
So I had my shower.
When I woke up,
You got the opposite effect.
I don't know. When I woke up, I wouldn't speak. I took a shower and then started. Oh, at least I can speak.
Yeah.
Fine.
Request this one wasn't me.
Yeah. I hear you.
That's good.
That's good.
Yeah.
Started. he's got very good feedback.
Send it to me.
He didn't have your email, so let me just forward it to you. Yeah, me directly and some of the others he knew of. Let me.
Yeah, do a like.
I'll do
try
a
and
reply.
with the CC.
That's. I'm just going to say plus this and suggest.
By the way, send it to
Yeah, that's fine. Yeah. Oh. I'll just shepherd the room.
I think part you're better in this dependency thingy. That he has 80 bytes. And he figured out it's far too much, so he reduced it. And 5 of them are pictures.
Make the discussion happen then. Good.
I told him we should.
Yep.
That's something which. Here's the standards, how they
I think we need to make the point. You want me to talk to that one? Sure, that's fine.
That would be good if you go.
Yeah,
This
that's
one,
fine.
Because that's the one.
That's fine. I can say, okay, we'll both stand up there then.
Yeah.
I just was wanting to make sure we get. Okay, fine. Yeah, I'll stand up.
But it would be good because this is a part which you are much better in than I.
On. Check that it's coming through. Okay.
I guess this is much better. Now everybody can hear us. Hopefully also the virtual audience. Do you get any? Okay. Yeah, it says on-site room is speaking, so I assume it arrives also to the virtual participants. And I guess then we give it a start, stop the conversation in the room. Directly getting more silent, that's great. Welcome to the first microconference session this day with safe systems with Linux. I start this with a short intro on this and give some aspects of dependable Linux systems. I will get support by Kate and sometime for one or two of the things I want to share. So it's about setting the theme. And yeah, when you think like, what about Linux safety critical part, which basically means like risk potentially to human life and other things. It's not so the security topic alone, it's really about functional safety. And we see that this is actually being used in safety critical systems today. So we see the examples of automotive where you bring it in. Sometimes it's hidden, not everybody's just making a lot of noise around it. And it's also went to space, it's used in satellites, other parts, and you find it also in a lot of industry, robotics, and so on. So it's nothing which is new. And that's basically it. But for many, maybe the definition of functional safety is new. And basically in the definition of safety, it's the freedom from unacceptable risk. It means that there is still a residual risk which you cannot avoid, but you try to lower as much as possible. Typically, try also to say like, it could be a risk to the human, but if it would be a normal scenario, the risk must not be higher. So if you automate something, you change something, it should not be a higher risk than the person would have when he would be alone or see. So, and it's about health of people, directly, indirectly, because of damage. And the functional safety is then the part of the safety that depends on the system, requirements, operating correctly, and responding to properly to the inputs. So that's the overall environment on this. And therefore, in functional safety, you expect that the software does behave as specified, which means like you have an understanding on what the software is. And we know that, well, we have sometimes the code as specification, and it could be sometimes good to just rephrase to come into points where you would say, here's something more needed, or do I have any evidence on testing something, verify that the code does what it should, and how do I make a connection? How do I trace that this is not changing over time? And yeah, then also how is the interference with other parts that you really know, like, well, simple example, your GPU is heating up, so your CPU is decreasing the frequency to just overcome the thermal things, and suddenly your system behaves slower while just doing more. So these are things, and think about all these events, what could happen. And for this, in industry, there are many, many different standards for automotive, medical, aerospace, space, and some other standards are there. It's like best practice developed over 50 years in industry. So it basically writes down what they have done, but maybe not for as complex systems as Linux is supposed to be, right? If you see original standards may think about 5 to 10K lines of code, which is nothing if you see the size of the Linux kernel. But all these standards still share a lot of similar best practices and demands. And it also shows that you need to know every part of your system and also the environment around it. So left and right, what's next to your core part of interest, maybe the Linux kernel as we are here. And therefore you do a lot of things about the requirements work, expectations, the testing, then writing the documentation around it that others know and can follow things and get the things traced together. And a few considerations.
Yeah,
Kate,
and so the key thing that was an insight for me anyhow is safety has to be thought of as part of a system. What we're trying to do is there's various needs that a system is trying to fulfill, and this maps into the requirements on the components into the system. And so those standards that Philip was referring to earlier all have assumed this type of model underneath them. And so our challenge becomes, when you go to the next slide, open source components do not speak that language. Okay? And so the question here is, how can we use these open source components, things like the Linux kernel, in a system and be able to do the right level of analysis in order to satisfy, the argumentation and convince ourselves it's safe to use, okay? Or convince whoever's making this product that the risk is low enough that you can use it. The Linux kernel, has processes, it has quality, it's been there for forever. But in some of what we're seeing is we are seeing company after company after company trying to sort of work their way around things and not collaborate on bringing a common expectation into play. Okay, everyone's doing, like I say, I talked to a company here in Europe, and they've taken in Linux kernel through 61508 already, but it took them 6 years. And none of that stuff's upstream, okay? So everyone is going off and redoing it, and we really need to start collaborating on how we can actually get the information in a way that when someone figures it out, we can share it. That is what we're trying to go towards. How we do this sharing is an open question. Chuck was talking about some of the aspects we're looking at and exploring right now, and there'll be more discussions today. If you want to move on, or if you want.
Yeah, so there are a set of challenges with safe usage in the Linux kernel. The interesting thing is we already have a lot of things there. So each patch that comes and is submitted to the Linux kernel has a reason. It could be a feature extension, it could be a bug, sometimes the bug is the feature. And you may even say like, okay, here, right, where you also just submit something, say, this is behaving wrong, but actually you return it. No, it's not behaving wrong. It's what I meant to do. So it's not supposed to do these kind of things. So this shows us already something about what things are required and what not. And it's a lot about the what and the why. You see the iterations of the different kernel version, or the V2 patch, chat, V3, something like this. So there you can also see that there is something there, and it's a form of a requirement, an expectation. something you have in there. And then if you you test it, most likely you will check it locally, you verify. So you basically fulfill all these kind of things also safety standards are doing, but it's not in such a way, it's very structured, but it's not in a such structured documentation way that you will have an easy way of access later on, that you can recheck this again. And this is not so, it is to a certain set systematically and still not completely systematically. And that's why we also come together here. Yeah. Right. And this is like this morning where we have a lot of different ideas on this. And I think the nice thing, as we talked about the system and the practical use, so Igor will start off with the practical qualification efforts which NVIDIA took. So this is something as a starting, setting us into the theme, then pointing to the program verification part to look into much more formal things. Also, how could we define specification, formal specification, improve the documentation within the kernel, and then bring things forward. Exactly. Thanks, Kate, for finishing off that. We stick in the time. And at the end, it's system engineering, as Kate said. So it's really like understanding how you use Linux, what part of the kernel, and so on. And by this, I think we don't, especially the intro, we just move on to get to Igor. I'll already bring up your slides.
And hopefully, I saw Brian's hand go up during this, but hopefully we can catch up on the questions and in the break or in discussion in the hallway as well, or feel free to bring it up if it comes up again, okay? Thanks.
Hello, I'm Igor, and I have a problem. When I start making slides, I make too many. So that's called condensed edition, because in reality, there's a second batch of slides, much larger afterwards. This is more geared toward making a hopefully interactive presentation. So for those who might not be familiar with it, ASIL B or ASIL Bravo is one stage of safety that is used in automotive. There are several. Let's say that this is not the hardest, but it's a starting point. And as Philip said, we think we know how to do it. Let's start with the question. The question is, okay, we think we know how to do it. We are willing to share it, like Kate said, but how can we do that in a way that doesn't wipe out the value that we have reached by achieving this qualification? Qualification rests on two aspects. One is, the value rests on two aspects. One is the ease of qualification, meaning that reaching any level of qualification is not trivial. It's expensive. And the value here is the fact that we think that what we do can be taken by a customer and easily brought to productization. The idea would be that we would contribute this to the Linux kernel so that everyone can do that. If in the process of doing it, the value gets lost, then somehow the effort becomes meaningless. Similarly, one of the important things is the fact that whatever we do to reach the qualification needs to be verifiable. Our users are in practice manufacturers of vehicles, robotics, also some sort of monitoring. To follow up what Philip and Kate said about qualifying the whole kernel, our answer is most of the time people want to use the Linux kernel because of its flexibility, speed of innovation, all of these features, which are very positive, but become a challenge when one wants to be able to take advantage of it on a very large code base. So our answer is do not try to apply to the entire code base the safety qualification. Instead, introduce mechanisms which allow to reduce the target of the qualification. And the idea is our mechanism become the main recipient of all the steps that need to be taken when doing a qualification. The goal is that these mechanisms would become part of the Linux kernel itself. So at that point, it wouldn't be anymore that we would be working around our way on the Linux kernel, but rather the Linux kernel would have a part of itself which would act as main recipient for all of the qualification steps that are necessary. The challenge there is when you qualify a component, not only the component itself needs to be qualified, but all of its dependencies. Therefore, there's a challenge in implementing these mechanisms so that they do not pull in everything else inside the Linux kernel. This is the major problem, because what has been seen so far is that many companies, for example, they even manage to qualify a Linux kernel, but by the time they're done, they have a very old version of the kernel, and then trying to repeat the same effort on a new version becomes impractical. One problem that I've seen is that, for example, if you try to upstream a component, usually one of the first requests is, can you do it in a way that is beneficial to also other components? If you have some code, can you refactor it so that it satisfies more needs, or it can be, it can leverage existing code, and then you just add a little bit on top, maybe making something more generic. And that's all right in general. However, the problem is when we do that, we fall back in the same situation of now we have pulled in the entire kernel or most of it. One example was, was the fact that now there is an ongoing effort of introducing some form of other space isolation. And if we look at that, we are doing something in spirit similar. However, typically when you are working within the kernel, you trust the code to be able to specify what it wants. And you might see problems at the security level, but then there are bugs that you want to fix. However, in our scenario, if we were to, for example, allow a function to specify what sort of memory it wants to allocate, that means that, for example, with the equivalent of a get free pages flag, that means that the function itself should be capable and trusted from a safety perspective of judging what it needs or what the execution thread that invokes it needs. Because sometimes the same function might be invoked by a thread which is safe and sometimes by a thread which is not. So instead what we do is, in spirit, follow the idea that we have capabilities. So each thread is given a specific set of capabilities, and by default, the thread would receive non-safety-oriented capabilities. So we would be able to identify which threads we have granted safety capabilities to. And functions, we tag them in a way that a function can try to exert the capability of the thread which is executing it. And by performing a convolution between the capabilities of the thread executing a function and the need of that function to have certain capabilities, we can determine what sort of memory we should grant the function. So this sort of a more implicit approach allows us to minimize the amount of code that we need to include in the safety qualification. One example is indeed memory management. Memory management is one of the most complex parts of the Linux kernel because you have different type of memory management. Most cases, it's distributed operation because you can have non-uniform memory architectures, per CPU caches, whatnot. It's very complex from a safety perspective to qualify something like that because, for example, on a multi-core system with many cores, many threads of execution, the fact that the scheduler might decide to run a thread on this core or on that core means that, for example, on one specific core, there might be more local pages available for being allocated. On another core, there might not be. So the same operation from a threat perspective might trigger completely different behavior in the background from the memory manager. And this becomes very hard to test. Even if one thinks about stress testing, it becomes practically impossible to claim any level of completeness of the testing done if performed on a sort of black box level. And if you don't do it as black box level, then you're back to the scenario where you have to qualify a lot of code. So our goal would be to keep the memory manager non-safe while achieving a safety compliant behavior. This is where the management of resources, I'm intentionally using the term resources because resources are memory, but we can think also about MMIO as a resource. It's just something that we want to consider from different level of safety. Interrupts also might be considered as a resource. You don't want a non-safe component to go and disable interrupt, which is relevant for safety. I'm sorry. Yes, okay. So one thing that we do for memory allocation, for example, is if we take the page level example, we perform end-to-end vetting, which means that one thread of execution might invoke a memory manager and expect to have memory of a certain safety level returned. So what we can do is by using pools which have been used to partition the resources, we can verify if the memory that we have received belongs to this or that pool independently from what the memory manager has done. For example, this is how we implement pools for various types of memory allocation. I'm sorry, the picture is very messy, but I didn't design the code. The Linux kernel has memory primarily divided into different categories. You have the linear map, which is just a representation one-to-one almost of the physical intermediate physical memory. I'm referring to ARM architecture. Intermediate physical memory into kernel space. Then you have virtual linear memory, which is vmalloc, which is another type of resource. And then underneath of it, you have the intermediate physical memory. I'm referring to a two stages MMU translation. Now, what we do is we partition them into address ranges, and each address range becomes a pool, which means that when we request memory of a certain type, by just comparing the address we received with the ranges assigned to each pool, we can assert if that memory belongs to the correct pool or not. On top of that, what we do is we also have a redundant bitmap where we mark pages which we have already seen as assigned, which means that if we detect that the page has been already assigned and now it's coming up again, there's been an error in the memory manager. We can do this on the PFN level, because those are, from the kernel perspective, they are unique. And then from the linear mapping, it's the same as PFN, so there's one-to-one correspondence. And for the virtually linear mapping, what we can do is we can check that the corresponding PTE where a certain physical page would be mapped, that it's empty. So by performing these additional checks, we can confirm that the memory that we received is safe. It doesn't mean that the safety of that the memory allocation went exactly well. You could think about just tossing a coin or rolling a dice and being particularly lucky. We can just verify if the result that we obtain is compatible with the safety requirement. But we do not particularly care about the correctness of the memory allocator as long as the output it produces is compatible with our safety requirement. So perhaps there is also this aspect which is slightly different from the typical expectation when one performs safety analysis about correctness. This is an example of how we modify memory allocation into pools. So in practice, by performing the convolution between the capabilities of the thread and the need of the function invoking the memory manager, we can decide from which of the pools available to allocate memory. On the left side, you see the typical case where you have local caches and then a larger amount of memory, which is used when the local caches are not available. So we just replicate those by introducing pools, which means that whenever the allocation happens, we can just use the information associated with the thread and the function to choose from which pool to get the memory from. Yeah, and pools are basically allocated to safety levels. Now, why are we doing this? Because we have memory maps. Yes, we are running different, we are using different memory maps in the kernel in EL1. That's a fairly new thing for Linux. This is an example of how you can see the use of these memory maps. Basically, by mapping a given pool so that it is not writable to by threads which are running at the lower safety level, we can safely share the memory across different levels by allowing only same or higher safety level than the memory to write to it. Lesser safety level, they can still read it, so exchange of information is still possible. One way, but it is possible. Anyway, what we are doing is nothing more than setting up tripwires. The expectation from a safety perspective would be that a lesser safety thread would not be expected to write to safer memory. So we just configure the MMU so that it triggers an exception if the unexpected operation happens. These memory maps, since they are related to threads of execution, they need to be activated on a per thread, per core basis. So in practice, whenever a thread is running or scheduled on a specific core, it will bring with itself the memory map it needs. And this is an example of how you can see these maps activated. And this is how it is across threads. And this is what allows us to have an easier qualification. The hope is that this has very little impact on maintainers. I see that I am running out of time, so for the sake of... Okay. Okay. The idea is that all of this I've shown can be compiled off. So from the perspective of a maintainer who's not caring about it, actually we want maintainers to not care about it particularly. The idea is most of it can, or all of it can be compiled off without any repercussion on footprint, performance, nothing. That's the advantage of the fact that we are trying to involve most of the kernel from the qualification. We are actively trying to not pull in part of the kernel from in the qualification, and that means that the kernel doesn't need to care much about us. There are just minor changes we introduce, like the fact that we need to apply tags to certain functions to specify which memory types they need, or some data structure they are turned into arrays of their former self. But when you disable this feature, it becomes an array of one element, so nothing really changes in practice. And some variables which we cannot variable protect, we need to wrap them with macros so that we can introduce redundancy. In practice, where you would have a normal variable, when our feature is enabled, you get two, one straight and one XORed, and whenever we access it, we verify the consistency between them. Yeah, this is an example of what we can achieve. We can achieve the fact that non-safe context cannot silently interfere with safe context. We get an exception if that happens, or we probe it and we verify that there's been a loss of consistency between the redundant information. And we can replicate that also to user space, because we can use the same pools also to populate the memory map of processes. So whenever you have a safe process that needs to run and be protected from potential unintended write operation from the kernel, the process itself will be populated by using pages that belong to a safer pool than the baseline kernel. What we bring to upstream, well, for those who are interested, it means that now it is possible to relatively easily qualify the upstream kernel if we manage to merge this. And this is not about achieving only AZ Bravo, like the middle level. It's about going all the way to the safest safety level possible. And there is no need for excessive documentation or processes. Like, I'm not against what has been attempted so far of improving the testability. That's all great, also the documentation. However, if we can focus those efforts on the part that we really need, we can achieve much sooner something which is usable, because then we have a very narrow focus on the portion of the kernel which are relevant to safety. And that's all. If there are questions or comments or objections.
How do you see this working when you're having to do systems, basically doing debug as you're trying to get things going? Have you got thinking about that yet?
One thing that I didn't mention here, but one thing that is necessary is we are also hardening the kernel stacks in the same way, because the stack is an important part, and it would be exposure to interference if we didn't harden it. And that compromises ftrace. It breaks it, we know it, and the idea is that we will restore functionality of ftrace with patching that makes it compatible with our hardening. So we know that we are breaking things, but we are also planning to fix them eventually. The idea is to retain all the ability. There might be some things that are harder, but that doesn't mean that they are impossible. For example, all of this keeps staying based on top of 3 or close to it. Like last week, I rebased it on 618. There were the sheaves and bars. It took me a bit longer, but a bit longer means that normally I just rebase it and it just goes straight. This time, it took me maybe half a day. So just to say that the fact that it stays isolated makes it also easier to rebase it.
So you've got a set of patches that are sort of doing this right now.
Yes.
How many, like, can you give us a feel of the size of the outer tree patches right now?
The way the code is structured, at least for now, is that we have all our stuff in completely different files, and then we have a selected set of patches which modify external ones. Mostly what they do is applying tags. I tried to use Cosinel, but didn't have the knowledge for this sort of operation, so perhaps that's something we need to improve. But in most cases, there are like here and there things where you have, for example, extra hooks at the beginning and the end of the function, which then we just resolve to nothing when the feature is disabled. And in some cases, like in the core of the slab allocator, there is a data structure, and what you see is that there's a bracket with an index that appears. So they are very non-invasive because, again, we would have to qualify a lot of kernel if we start modifying it. It's in our interest to be very non-invasive.
And is there a chance for maintainers community to also take a look at the patches, or is it mainly kept silent video so far?
We are in the process of eventually releasing it. Besides, it won't be pure kernel, so we are also in the process of discussing exactly how to arrange it. Maybe Elisa can help, because, for example, to achieve safety, there are patches for user space and a little bit also for hypervisor. So the idea is to use an open source hypervisor as a reference implementation on top of which we would deliver also the hypervisor side of the patches. So eventually, yes.
Okay.
Okay, thank you.
Presentation is here. See the presentation?
Yes.
And you can use either the button or go left, right. So just see?
Okay.
Yeah, you're good?
Yep.
Okay.
Thank you.
I'll stop you. So you will see the 5 minutes warning. 10 minutes beforehand.
Okay.
So that we have at least 5 minutes for question. Right? So you get the feeling 5 minutes really. And when I say stop, then you should really stop. And it's 5 minutes.
Okay. So when I see stop, I should. Okay, I will.
You start with 5, count down, and if you see stop, then you should really stop.
Okay.
Thank you.
So, okay, let's start. Hi, good morning. I'm Keisuke Nishimura from INRIA, an institute from France, in France. And I will talk about our ongoing work about verification for the Linux kernel, formal verification to the Linux kernel code, applying programming verification to the Linux code, challenges, practice, and automation. This is a joint work with my supervisors, John Pierre-Lozzi and Julia Labo. So first of all, the Linux kernel, which is an operating system, and the system software should always be run properly. But in reality, we have a lot of bugs, unfortunately. Some bugs are somewhat possible to detect. For example, null pointer differences. They have a clear definition, and many people try to detect such kind of bugs. But about the semantic bugs, it's very hard to detect it. People try to detect such bugs using, for example, code reviews or tests. I know there's some efforts ongoing about testable specification, for example. And here, our message, our takeaway today is that applying formal verification to the Linux kernel is still hard. We admit that, but it's becoming increasingly feasible. So yeah, that's our takeaway. So please chime in if you have some comments or questions in this talk. So here's an outline. So I will start with what is a verification. Yep. So now we will introduce about the deductive program verification. It takes formal specifications and programs, and then the verifier decides if a program meets a specification or not. So we need formal specifications. Formal specification can be defined something like this. Before the program, we assume some conditions. We call it precondition. And after that, the state of the program meets some certain kind of constraints. We call it post condition, which means that if this precondition holds, then after the execution of program, this postcondition holds. So that's the specifications, the form of specifications that we want to use. And so for the verification, of course, it's possible to represent the specification as using natural languages, English. It becomes like if the variable x is more than 1, then after the execution, the variable x is more than 2 or something like that. So yeah, it's possible to represent it, but what we want to present here is to use the more formal representation of specifications. So we call it formal specifications, and formal specification looks like this. It's somewhat in the middle of the programs and mathematical forms, or maybe kind of English. It's in the middle. And the good thing to use formal specification is, obviously, it's less ambiguous than like the natural languages, and also it's possible to apply a machine check for their correctness. And of course, the limitation, the downside is it takes significant effort. So here, the machine checkable means, for example, we can check the completeness or disjointness of specifications. The typical specification looks like this. So if condition X meets, then the result would be 1. The result will be 1, and if another condition meets, then the result becomes blah blah blah, something like that. So here, maybe people want to assume the disjointness among the conditions, or maybe people want to complete enumeration of those conditions. But achieving it manually is a bit hard. But we can systematically check the correctness of specifications. And also, about the correctness, it's a bit hard to keep maintaining it. Here's an example from ftrace event enable and disable functions, and we found it in the specifications. We found it in a mailing list, and I'm not very sure about the. I'm not very sure that I'm referring to the correct version of the Linux implementation with regards to this. With regards to the specifications in the mailing list. So please let me know if there's something wrong or some discussions. But what I found is that in the proposed specifications, this break was not considered. This break happens after the. So this break is triggered when this function pointer calls fail, and this is obviously a minor pass, and it's not I think it's not a fast pass or very popular pass. But when writing the specifications, one needs to consider detail or minor part of a minor pass, or one needs to be very familiar with the let's say the dependence. If the query functions may fail, or this function may fail due to this reason, or blah blah blah, something like that. It requires a lot of knowledge, so it's very hard to represent it. And that's why we also that can be a motivation to automatically checks if the specification is correct or not. Yeah, that's about formal specifications, and then we will quickly introduce how the verifier works. So the verifier does backward reasoning from the post condition. they guess what's the weakest precondition, and then if it checks if the given precondition implies the weakest condition. However, if we encounter a loop, it's very hard to apply the backward reasoning. That's why we need to manually annotate a program to using the invariants. Unfortunately, there's no silver bullet to solve this problem, so manual work is somewhat needed. However, in the case of Linux kernel, there are some patterns. They follow some patterns. The loops in the Linux kernel is somewhat simple, so maybe we can apply some certain degrees of the automation. So we will revisit it later. So then let's see some example about the case example of applying verification to a small function called is called idle in the Linux scheduler. Is called idle checks if all CPUs in a given core are idle or not. This iterates over CPU IDs in a CPU in a specific corresponding CPU mask, and then checks if all CPU is idle or not. So, for example, if the parameter is CPU2, and here is a example representation of CPU situation, it checks from the check starts from the CPU 0, and then it finds CPU 1 is not idle, then it returns false. But in the case of idleness, then it can reach to the final statement that returns true. So how can we apply the verification to this function? Yep. So as I said, we need to write formal specifications. The specifications can be like this. It looks like programs, kind of programs. And now we will define. We will define these predicates. So here's the definition. I don't want to go into the details of this predicate for now, but it looks like this. So it means that this predicate represents the state, the idleness of a given CPUs, and using this predicate, we define the idleness of a core, a group of CPUs. Here, for all quantifiers, if CPU I belongs to the same core as CPUs, then it says that the idle of CPU, idle CPU of I is also true. That's the kind of mathematical definition of idle core. And also, we need to remember that we need a loop invariant. We need to manually write it. It iterates over the CPUs in the given core. So that's why we can write the invariants like this. So it states first states the range of the index, and then it captures the effect of the loop body like this. Yeah, of course, it's manually writing those specification is hard. So we have some approach to automate these types of tasks. So finally, let's see some automation or more practical part of applying verification to the Linux kernel. First, here's ideal workflow for the ideal workflow for the kernel verification. We select a function, then write a specification, we annotate a loop, and finally verify it. That's all. But for example, it's very hard to directly apply it, unfortunately. For example, So when I write a specification, I don't know, yeah, this is not a simple task. For example, we have no concrete idea what code should be provided to the verifier. So one can say that the entire source code can be the input to the verifier, but the entire source code contains a lot of unnecessary dependencies, or some of them hinders the applying the direct verification, or maybe for example you don't need to verify something related to print K or PR info or something like that. Maybe we want to ignore such debug functionalities, or those kind of auxiliary functions. So our automation for the preparation. So sorry, we propose automatic preparation of the verifiable code. Our solution is that automatically extract a minimal but self-contained file for the verification, and then we replace some dependencies to make it more suitable for verification based on the user-defined instructions. So in the case of is called idle, the fair.c is very, very large files, as you know. And also after the macro expansion, it will become very, of course, it will be very, very big, files. That is very hard to handle manually. But our extracted code is about 60 lines of code. It's possible to somewhat manually work on this amount of code. So indeed, it has it depends on 9 macro or 4 cores. There are a lot of dependencies so correcting them manually is time consuming. And also loop invariants, about the loop invariants. Again, so we have no silver bullet to solve all the problems related to loop invariant inference. But for the specific context of the Linux kernel, we may be able to automate this kind of work. There are some idiomatic usage patterns in the kernel. For example, for each CPU iterates from iterates over CPU IDs, and it used a lot of many times. So it follows some patterns. It follows some patterns in the loop body. So by capturing such patterns, it's possible to somewhat automatically infer loop invariants. That's our ongoing work. So finally, but I think it's very important part. We need to apply the formal verifications. We require a formal specifications. That can be a big problem. We do not know the formal specifications of most functions in the kernel. And to make it clear, we don't ask developers to write we don't ask developers to write formal specifications for all functions, but it's very hard. Formal verification can give a very confident formal verification can give high confidence about the safety, or the safety, especially about the functional correctness. However, the cost, it costs a lot. So we want to make a balance between them, and also the Linux kernel develops, and the evolution of the Linux kernel is very quick. So maintaining formal specification, it might be very hard and impractical. On the other hand, once a formal specification is written, then the specification can be somewhat reusable for the updated versions. So in this case, once you spend some time, then after that, catching bugs may become a bit easier using the formal verification. Yes, this is the summary of this talk. First, this talk was about the deductive program verification, and it requires formal specifications of pre and post condition. Based on pre and post conditions, and it requires manual annotation of the loop. That can be a limitation, and however, it can give us some high confidence about the safety or the correctness, especially the functional correctness of the program. Towards the practical application, automatic preparation of the verification and inference loop invariance, that can be somewhat achievable. So that's our current ongoing work. And also, we require, to apply this, we need a formal specification. We are trying to write formal specifications, but also, but still it's very hard. So that can be another limitation, but also it can be a very good chance towards the more safety, the safer systems using the verification. That's the end of this talk. Thank you for listening.
Thanks for your presentation. I'm curious if doing the formal verification only at the individual function level is enough, or if you have to do like formal verification also like a feature level and maybe subsystem level as well.
Thank you. Yes, that's very it's very hard, but basically we need I think we need a feature level. I think we need a feature level or component level verification. But it doesn't mean that you need to verify all the functions in the components. For example, we maybe assume the correctness of some auxiliary functions, or maybe we can ignore some auxiliary functions, like print k, for example, where maybe it might not. It may be irrelevant to your functional correctness that you want to apply. So.
So I wonder if there is outside of the Linux kernel maybe like already a way to describe a good specifications for like verification. So or is the kernel so special that it needs its own language to describe such specifications for verification?
Yeah, thanks. Actually, it's a very interesting question because, sure, outside of the kernel, there are a lot of, maybe not a lot of, but there are some practical application that is verified, formally verified. Some of them are written in C and some of them are written in more functional languages or something like that. But in principle, they are designed verification in mind of the verification. However, in the case of the Linux kernel, at the level of the design, verification is not considered. So I think it's very big. This is a very big difference. So applying the verification to such software requires some work, maybe more than software designed for verification.
So I think that's what you answered was about like you designing code for verification, and the languages that have like Daphne or something like that have been developed where you design the code and you do the verification at the same time. But the other aspect of the question is like, how can we make specifications be at a understandable and writable and readable level? And I had my own experience where the first time I tried to formally verify a function, and actually another colleague tried to formally verify the same function, And we both wrote the specifications at a very low level, and we both failed just because we got lost and the specifications were too complex, and we just really had the feeling that this was going to be impossible to verify. I mean, that's always the issue. We have these tools that try to do things automatically, and you always are kind of reaching the boundary of what they can do. But then I tried again later on, a little more perspective, something like that, and I defined some macros, and that made all the specifications much more readable. And then everything went smoothly, and I was able to prove the function I wanted to prove. So these were just macros, so they were just expanding to what the specification should have been. But on the other hand, if I tried to take those macros that were appropriate for that function, and I tried to work on some other function, I thought those macros were wonderful. They really help things out very well. But when I go to some other function, then the macros don't have quite the right arguments, and I need to adjust them a little bit. So I can't say that those macros are the perfect language for writing specifications. And I think we need a lot more experience to know what are the right abstractions. What are the abstractions that we can actually reuse on many different functions to be able to express the things that we want, but have the things that we express be readable both for ourselves and and also for other people.
So when you say obtaining good specifications, is that just we're going to be inventive, or you have a way of getting them, or that's future work?
Obtaining
Obtaining good specifications, the last line of your slide there.
Yeah, it's a future work, or I don't know. I don't have a very good clear answer for that. Yeah, of course, inferring from the existing code is somewhat possible, but it's very dangerous. The original implementation may contain a bug, then the inferred specification also may contain a bug in this case. It's very, we don't have the clear answer to how to do that. How to do it.
If you infer from specifications, it's very useful in that you can find bugs. What you can't do, and I don't think you can do it anyway, period. What you can't do is actually prove the program is correct because you don't know what correct means.
Yeah.
Thanks. So I guess we move on. We're just at the top of the hour to change. Thanks a lot. I'll give you 5 minutes warning, 10 minutes before the end, right? So
10 minutes before the end,
I give
okay.
you the 5 that you have enough time to finish off, and we have still 5 minutes for question, hopefully. You can go right, left, and then go.
Yeah. Okay, can you hear me? Yes, okay. Apologies, I have a pretty low voice today, so I'll do my best. Okay, so you see? Okay, so I don't know if yesterday you came to the referee track, to the talk from Chuck. Yeah, here it is. So today, basically, we'll continue the discussion, and I will mainly present what we have done from a code contribution point of view, and I'm effectively looking for suggestions to address basically the comments that we got. So it's going to be a bit more open discussion and technical session. Okay, so yeah, so this is basically based on the work that we are doing in the ELISA architecture working group. So if you want to join the discussion in the long term, please join us at the architecture working group. And this activity has been mainly led by myself, Kate, and Chuck that are here. Okay. Okay, so what we discussed today is first we will I will go quickly through the requirements template that was anyway presented yesterday by Chuck. Also quick through the trials that we did on the tracing subsystems. I will focus a bit more on the trials that we did on DevMem, where we got the main comments from Greg Harman. And finally, we'll have an open chat to see what to do next. Okay, so last plumbers. We had a session about improving the kernel design documentation, where we explained why documenting the code is important. Okay, and indeed there are some aspects to consider. Indeed, new developers and security experts can verify if their proposed modifications are coherent and consistent with the intended behavior. We would have probably a reduction of buggy patch proposals. So maintainers should have, a more effective, maintenance process because of, less bad contributions. And indeed, testers can test the code against this documented behavior rather than, based on their understanding of what the code is expected to do. Okay. So a tester could mislead a bug for a feature by reading the code. So let's plumbers, and I see people here that were also present in Vienna. We kind of agreed that low-level requirements are important to properly maintain code documentation. And the maintainers that were there, they asked for the semantic aspects of the requirements to be maintained in line with the source code, whereas all the other aspects should be maintained outside in a sidecar file. Okay. Indeed, whatever we propose should be compatible with what already exists. So today we have the kernel doc headers, we have all the existing kernel doc guideline. Whatever we propose should be an extension that is backward compatible effectively. And and indeed the requirements definition should be supported by automation. Okay. And today I will not talk about the automation. We have a strict doc chat the session about that later. Okay. Okay, so this is the template that also Jacques presented yesterday. Today we'll talk about the field SPDX requirement text. Okay, so that is effectively the semantic part of the requirements, and and the key question is, how do we write this semantic part? So initially we did some trials. We went to the ELISA workshop at NESA. Steven Rosted was there and he said, hey, look, I don't think the maintainers are ready for, to accept all these requirements, template and stuff. We should show the value first. So please start, documenting the code without, this formalism. So basically focus on the semantic part using the kernel doc headers that exist today, show the value, and then maybe, together with the maintainers, we can also talk about, the more complex template, with all the fields and stuff. I said, okay, let's do it. So what we did is we mainly worked on the tracing subsystem. We found a bug. It was also backported to LTS. Good. So we show like the value to some regard. We identified a redundant flag. Steven reworked the code of, I don't remember the function, but basically, he reformatted the code. He got rid of this redundant flag that was there. So we optimized the code. Okay, so good, everything good. And also, we figured out that it is easy to mislead a feature for a bug. So basically, we realized that, with the current implementation, it was, it was if the trace events were read 1 byte at a time, there could be a non-atomic read that was leading to a corrupted event. And, we tried to fix this. And Steven said, do not fix it. I don't expect anybody to read events 1 byte at a time. So what we did instead of fixing this, we documented these assumptions of use so that, the external user now knows how to read trace events. It wasn't written anywhere. Okay, good. Then we say, okay, great. Then let's try it out on DevMem. Let's see what Greg has to say about this. Okay, and so we first send out a submission, trying to document the DevMem functionalities using kernel.headers. And Greg said, you used a pretty strange language. Where is it documented? Where is this formalism specified? And I said, oh, I missed that. So what I did, I submitted another patch set wider. So, and where the first patch is contains the guideline that tells how to write these semantic code testable expectations. Okay. The second patch contains, the DevMem specification, and the third patch contained the K-units that were written by Alessandro, that is here, by the way. Not the K-unit, the K-self-test at that time. Now, for the next patch set, this will be converted to K-units, sorry. And, but there was probably some misalignment with Greg. And I said, basically, in the first part of patch 1.3, we explain why we are doing this and the high-level goals. Do you agree with this? I mean, with the goals. Are these clear? And they said, no and no. Okay, you can read this, right? And they said every in-kernel API documented in a formal way like this, or a subset. If a subset, which one, how many, and who is going to do the work. So it looks like, a bit of opinionated reply, right? So he said, for some reason, the Linux has succeeded in pretty much every place. Why are we doing this? Why are we even talking about this? Okay, then I said, hold on a sec. I mean, I thought that, last plumbers, we already discussed why we are doing this, but maybe I was wrong. I don't know. So now let's go to the open discussion, right? So why are we doing this? Already, so this is the copy and paste from the first slide. Okay, so the reason why we are doing this is because, new developers and security experts can verify the proposed modification to be coherent and consistent with the intended behavior. They would also understand the code behavior and constraints for proper usage without going through the complexity of the function. And they can also, and testers can test the code against the specification, not against their understanding of the code. So this is the idea. In general, indeed, the technical depth associated with the Linux kernel would be reduced. Okay, so this is the main reason. I mean, you can also find other reasons from a business perspective, but these are beyond the value, the strict technical value that we are giving to the community. Okay. So how many APIs and how? How many APIs? We don't know. I mean, I cannot tell. I mean, I'm waiting for Igor to publish the source code, for example. So really, depending on different use cases, the number of APIs to be documented may vary, right? I mean, from Red Hat, we may have a certain need. From Boeing, we may have different needs. NVIDIA, maybe a little need, just little, right? So it's at least just a bit. So NVIDIA is a good starting point to try out this because, you know, they have a small code base now. So it's really, I mean, it's not an answer that we can give right away, how many API, really. What is important, however, is that we are not mandating a different model to contribute code into the Linux kernel. We are not saying every new patch has to come with documentation. We are proposing a way to extend the current contribution model with optional documentation if needed, okay? Optional documentation and tests that will be linked to this, okay? And this is probably the key point, in my opinion. Okay, so what we are really trying to propose. And who's gonna do the work? Igor, me? No, Igor, maybe not, but somebody else, let's see. But so whoever has best interest, you know, in pushing these documentations and associated tests stream, really. So this is, you know, this is how, you know, who is going to do the work. And indeed, you know, I hope, I mean, today, theoretically, you know, kernel doc headers should be welcome by maintainer, right? And also associated tests. If there is any maintainer that here that has a different opinion, you know, that you don't welcome kernel doc headers and tests. Yeah, anyway, so now I will take, you know, here, I will stop for a second, and then I will start again. I have another 3 slides where I want to discuss about what we could do next. As in, what do I do with patch v3? But please, let's have first an open discussion.
So I think the question of how many APIs and how or especially how many APIs is kind of complex because, I mean, one approach, which I think is what was kind of pushed yesterday, is that somebody is trying to understand some part of the kernel and then they feel motivated to write because writing is kind of a helpful intellectual exercise. And then the whole goal of the process is to have that person have a place to put the information they have written down in a structured way so that they themselves and other people can benefit from it in the future. So that seems wonderful. I think I at least write down things all the time when I'm trying to understand them, and then I lose what I've written down, and then that's not great.
Sounds like the message was clear. Thank you.
You're welcome.
Keep going.
But that's kind of an after the fact thing. And maybe we need something that will be more a priori. So I wonder if we could somehow harness AI to try to figure out what are the parts of the kernel code that are hard to understand. I mean, I have no solutions to propose,
So,
but that's what AI is good for somehow.
Yeah, to that point, yesterday we had there was the kernel summit track. The first session was held by Jonathan Corbett, and he discussed about the usage of AI in also in documentation. So, and the question was, how do we cope with that? And in my opinion, the burden of using AI should be down to the single contributor. As in, if the single contributor find an effective way to use AI that will still make his contribution trustable to the maintainers, then fine. If you start to submit trash, right, something that doesn't make sense, you will be soon blacklisted or become untrustable source of submission, I think.
Okay, yeah, I mean, that's fine. That's not what I was suggesting at all.
Yeah, it sounds like you
I
were saying
was
use
not
AI to find the places to look at.
Exactly.
Exactly.
AI
yeah.
discovers that
Sorry.
select idle sibling for a function
sorry,
that I know
sorry, I
well
didn't-
is a very hard function to understand because maybe it refers to a lot of concepts that are not well documented or something, some property about that function makes it very obscure.
Yes.
And so then a human can go in and maybe a knowledgeable human
Yes.
can go in and write down the things that they know.
So AI to analyze the code effectively.
Yeah, to find the places that need to be better documented.
I would like to reply to that. So at least with our approach, there's no need to rely on AI. Strange coming from NVIDIA, but we tag exactly. We can programmatically create a list of functions which are necessary to be qualified and therefore could benefit from that approach. The reason is because we tag them by the idea is we rely on the MMU to generate exception when something wrong happens. So our argumentation is if we forget to tag a function, when it tries to access and modify something which is safety relevant, you'll get an exception. So we need to tag it to grant it the capability. Well, it's a bit more complex than that, but in practice, we can generate a complete call path of those functions which are given the capability of generating interference. And therefore, we can produce a deterministic list of which functions need to be validated. So the problem of where should I start from? I think we have an answer for that.
No, understood. I mean, you have a pretty small code baseline to be documented and tested from the.
We have let's say, our implementation, which needs to undergo whatever requirement-based approach is necessary, and then it relies on a small part of the kernel, and that's where
Exactly, I understood. So fine, but this is why it's a good starting point.
No, I would say that there's not even a need of guessing.
So when I enter some path or some areas of the kernel I haven't been before and I have a hard time figuring out, then I usually add documentation so the next person will have it easier. But some part of that is that I have to fix documentation because it got stale over the time. And so even to the point where I think sometimes no documentation is better than wrong documentation. So, and this is why I want to emphasize Greg's point of who's maintaining that. It's not about adding only, about also maintaining the correctness, especially if you want to use that information as part of some kind of verification.
Yeah.
Because just I, as a maintainer of a subsystem, wouldn't like to take this extra burden of making sure that's all the time correct.
I kind of agree that stale comments and stale documentation is worse than no documentation. But on the other hand, if we have formal documentation, you can validate it automatically if it still matches, and it will whack people over the head if they change the code and do not update the documentation accordingly. That's the important point. I mean, that's why our documentation gets stale, because people are lazy, and nothing forces it to actually update stuff, except for if you have to add or change a parameter or a member of a struct and you do not document it or remove it, then the kernel doc parser will yell at you. But for a textual functional description, there's no way that we have any information if the comment is correct or not.
What I meant is that we need people doing that, maintainers, other than me, because that's what I'm getting at. Who like?
Well,
I'd like to, all I'm giving this back to, so one of the things we've got in the sidecar is ways of hashing and finding out when something gets stale. And so if there's a patch applied to the code and there's tied to an expectation in the formal documentation, then we can actually find it and actually signal it to the maintainers that something has gotten stale and look at it again. That's one of the things we've got in the sidecar, but that isn't what's in the code.
I don't know where to start. I'll just throw a few things out. One thing, the hashing, I mean, sounds that I really do not want to get whacked over there with a hash every time somebody has a white space change to a function. And I don't want to tell people not to do that. Anyway, the point, if we get to having formal, I can see it, because then if you make a change and it doesn't match, you get yelled at reasonably as opposed to randomly. Okay. And yeah, tokenizing, you can do that, but still there's a lot of changes that, you know, yelling at me to say, hey, this might have changed, go look at it. Hey, this might have changed, go look at it. Hey, this might have changed, go look at it. I'm going to tell you where to go jump pretty quickly. All right. I'm sorry. The other thing is I apologize in advance, but I was at the session yesterday and I just could not shake the feeling that you guys want to fill out something like I did back in the 80s on the old DoD standard 2167A, where you have to paper down document all these little things in each function. Well, you say that, but that's the only thing that makes sense from what I see here. I mean, I wasn't born yesterday, and that it keeps coming, that keeps whacking me in the head, okay?
Microphone to you.
Believe me,
Sorry.
I work in that industry. I know exactly what you're referring to. Okay, this is not for that. This is for technical debt for maintainers to tie intent to code. That's what the hashing is all about.
Well, that's wonderful, but technical debt that whacks me over the head with a lot of false positives, technical debt, I'm going to throw out the window. Okay,
And that's
sorry.
fine. As a maintainer, you don't have to run the Python script that calculates hashes and tells you the 5 that you need to look at. There will be plenty of CI and automation. We have kernel CI, right? It will run that, and it might tell somebody you might subscribe to automation.
And it will whack me over the head, and I don't like
ignore
that.
it. You can choose to not subscribe. Good. I think Julia is.
Yeah, pointed here first.
I wish the device tree maintainers were here, because that's about as formal as we have in the kernel right now,
Yes.
and they still struggle with DT bindings check and all of that. It still creates a lot of whack-a-mole jobs for people to go fix every time they tighten up the rules. But I think that's the best we have in the kernel right now.
I would love to discuss it further in the home
Comes
track.
close enough to like a formal definition.
So for these hashes, the idea is that you have a function and you have the specification, and there is some hash that connects the function to the specification.
There's actually 2 hashes. One is immutable, so it's established when you do it first. So you can trace into that forever. And then the other one floats with the changes.
Okay. But an issue is that documentation may refer to other functions. And so how are you going to keep those things connected to each other?
So we basically have a rec ref, so you can basically tag something that refers to another area, and by using the identification key that's associated with the rec. So yeah, we recognize very clearly that multiple parts throughout the kernels work with a certain concept, and so we've put a pointer into the information that we can basically link things together. We need to start, we want to start getting closer to this so we can start to prototype it out. And that concept was put in there. I was pushing for that concept because I've seen it way too much.
Okay,
And so that's it.
So again, just also speak to where the industry would not be headed. The kernel is remarkably polymorphic. It's really neat. Okay. But you would never do this in like a pure ground up DoD project, right? It's very declarative. It's for the specific purpose. This is another reason why there's just, that would be an endless tar pit. Nobody wants to get to what you're describing.
Well, that's one of the reasons I'm not very happy with you right now, because I know that.
Yeah. So all I would say is give me the opportunity.
And again, you're telling me a lot of things. You're showing a lot of stuff over the horizon that might be useful, but you're putting a lot of weird load on me right now. And you throw that in the CI, and then I'm going to get hammered with the CI thing.
What we're trying to do right now is figure out what is the language to use to express an expectation. Okay, but there's a whole degree of very strong formalism all the way through to a very natural language that doesn't give us what we need to link to the testing.
Kate, I've been using formal verification since 1993.
I know you have. I know, but basically, when we start looking at the formal verification language, we basically get pushback from other maintainers.
Well, of course.
And so we need to figure out how to thread this needle. Okay.
I mean, I had this discussion internally recently with Tobias. So the point is, you need to start somewhere. And for example, what Sasha is doing with the SysCal ABI documentation, which aims for a formal specification of the syscalls, start there. And if you can show benefits of this, then you have an argument. If you start somewhere in the leftmost corner of the kernel and ran into the wrong maintainer, you get nowhere. So you're trying to solve the big problem in one go. It doesn't work. I mean, that's like RT. Yeah. It takes a long time.
I went through that with you. Okay. Yeah. No, but we're trying to find an angle where we can actually get and start making traction.
Yeah.
And part of it is the language.
There's a high interest in getting the syscall documentation very formally done.
Okay.
For purposes like fuzzing and functional testing, more automated or more directed fuzzing, if I remember correctly, Sasha. So this is the point where you can work together and just get it done. And then if you can show the benefit, hey, this found $12, nobody can argue with you anymore.
Yeah, like we've
if you
we're finding when we do this process, we're trying to basically share the analysis. The same way you share code, we want to share the analysis.
Yeah.
In a way, and we find bugs.
So when we did it with Steve's code, we looked at 10% of one file and found 2 big bugs. So plenty there. Sampling is high. Yeah.
All right. So I'm not a kernel dev, so maybe I have no business being here.
You have every right to be here. Keep going.
So the kind of comments I like, are the stuff you see in like Python and Rust code, doc tests, which are like examples of the function usage. And these can act as test cases, so they can actually be run, and you can use it to verify that the function is still doing what it's intended to do. So like a lot of devs, I don't like to read big lines of prose. I don't want to know what your interpretation is. I just want to know what your intent.
And that's called pseudocode, and it's not useful. It's not value added. So yes, the intention is what's more important. Also, with highly modal functionality, it's like you need to say what's going on behind the scenes that's driving this thing internally that's not obvious.
The assumptions of use.
Assumptions of use.
Yeah. Assumptions of use are not always clear, especially as functionality goes between multiple files. And there's interactions of context and what the context is being assumed at various points in time. And so having a reasonably structured way of expressing this will hopefully remove some of the bugs, quite frankly.
So
hold on one more time. I want to go back to what Julia brought up. Anytime you learn something that was hard to figure out about the kernel code, like irrespective of everything being discussed here, when you're reverse engineering scheduler behavior to do real time 15 years ago, right? You just are learning these really hard nuggets of information. That's all we're doing, is we're making it easy to keep track of that and then lending it to other functionality like keeping synced up with test and all that. I don't want to lose the message for the trees and talk about DoD stuff and all that. I want everybody to, this is a place we define what a thing looks like. We're all now able to use that thing. That's more what I'm getting at here.
This is not an easy problem. I mean,
Clearly.
I'm seeing, when I say easy problem, I mean, even talking about what it is. I mean, if you go in every stupid function in RCU, you write the RCU grace period rule every time, you're going to hate yourself and I'm going to hate you. Okay. So you guys, I mean, we have to be a little bit more rational and careful about how we're going into this.
Agreed.
Going and telling me I have to do this stuff, is CI is going to beat me over the head every time I tell you.
Oh, no, please don't.
Way,
please
get out of
don't,
my face.
don't.
I'm going to yell at CI if they do that.
No, you can ignore all that.
I will unless it shows up, and then
That's
I will
fine.
not ignore it. Believe me.
but sometimes it might make a point. Like, is this what you really meant?
Make a point, maybe not the one you think it makes, but it's going to make a point, my friend. Other questions?
Okay.
Thank you.
I want to show you. So after the feedbacks that we got on the mailing list, I had a chat with Greg. Okay. So and he said that the main problem for him was that this patch set was proposing a guideline on how to write the long description of the kernel doc header. So he said, use a simpler, natural language for the specification of the devmem functions, and resubmit without, all the specification about, without all the guideline to specify testable code expectation. So what I understood from the chat with him is that different maintainers have different opinions. And this is also clear from the discussion that we are having here, right? So what I'm going to do is, step one, I will remove for now the documentation guideline from the patch set, because it seems that we still need to experiment on submission, maybe, also as Thomas, you're suggesting, like the syscalls, right? So we need to experiment on submissions across maybe drivers of maintainers that, are wishing to collaborate on this experiment on syscall. And one of the experiment is probably, also experimenting the Sasha's patch set. And thank you, Sasha, for, I had a chat with the Sasha last night, and so he's on board with that. So, and thanks. And so first of all, the first thing, I will remove this. Okay, we are not ready yet to accept any formalism. We still need to do more experiments. The second thing is, I need to define minimal syntax constraints to allow traceability between test cases and code specification. So the bare minimum that I need to write specification as a bulleted list, and constraints of use like as a bulleted list. Okay, so that when I write k units, I can somehow trace back between k units and the different specifications. So this is a very simple expansion on the kernel doc.rst that exists today, where I'm saying, when specifying testable code behavior, the longer description must contain a paragraph formatted as follow. And it's just a list of bullets, nothing more, okay? So I'm not asking anything else. And step 3, experiment according to the maintainer wish. Greg likes a simpler bulleted list. When we talk to Steven Rosted, it seems that he also liked maybe a bit more detail. Paul doesn't like any detail at all. So, so basically, yeah, the idea is that let's take a step back and let's try to to experiment more, and trying to show more value and get the right guidance from the maintainers effectively. And yeah, any last question on code?
So if we have maintainers who would like us to take a look at your subsystem and do some reverse engineering and experiment with ideas, means you're willing to at least take a look at what we're doing. It's a good use of our time to know that you're willing to engage with us. Come talk to us.
I offered yesterday evening to point you at two specific areas to look at still stands. Up to you to take it or not.
Yeah,
Will the maintainer engage with us when we make proposals?
he's the maintainer.
So that sounds like a yes, right? Cool. Wait, was that a yes? That sounds like a yes. Fair-minded engagement, that's all we ask.
Right.
Okay, we are just for like the time itself, we're in the break time, so it's a nice discussion. I just want to give those who feel like they're thirsty or whatever, the hint that it's the official scheduled break, but I think the discussion is great, so keep it going either in here in the room or where you like.
Very grateful for the discussion. Thank you so much, you guys. You guys are awesome. Thank you. Thank you.
Can I see this? This is amazing.
Yeah, we usually throw it, but
Yeah.
it's being all the way in the back. It's sort of odd.
Yeah. So I don't want to be the one.
Yeah, okay. Yeah. I think everyone knows where we
No, I got it. Yes, I put it away.
Here. I missed to tell or at the beginning.
Yeah, I saw he was rushing through several slides. One by the blur.
He said before, check the uploaded slide from him. He said he has 8 prepared, and then he made the short version of it, which was this one. So he has not 2 versions uploaded, first a shorter one, and then a full. I think mine is a dozen. Yeah, that's a full number. It always depends how much you talk and how much. I bring it up for you. Sound check works. We'll continue with the next part from Matt about K-unit testing insufficiencies. So, stage is yours.
Great. Hello, everyone. I'm Matt Whitehead. I'm with Boeing. Today, I'm going to be talking about K-unit testing insufficiencies. And first thing we'll talk about is, well, what do I mean by that? So agenda, we're going to have intro. We're going to go through kind of a demo of writing a unit test, a K-unit test, and showing the particular set of insufficiencies that I'm trying to discuss today. So insufficiencies become apparent when we're writing a lot of tests, and we're writing highly detailed tests and testing small isolated units. So kind of referring back to some of the earlier presentations about some of these safety related topics, and actually interestingly the earlier presentation about formal verification and isolation of small units so that you can test those specifications in a smaller environment that's more emptied of dependencies. That's where some of the issues with how K-unit tests come into play. So that's when we're talking about the scenarios above, that's basically what we're describing, right? We're writing tests there. We're trying to verify intended function, functional safety, and continued functions and security. So here on the left, I have kind of a really simplified block diagram of the process you go through when you're doing some testing, right? You write tests, you build tests, and you execute your tests. So what we run into with K-unit is that the way the framework is built, and necessarily because of the way it has to execute in the context of the kernel, is that you're missing some of the tools that you have when you're doing conventional unit testing. So things like faking and mocking and all these items you use for dependency management and decoupling from your dependencies when you're doing your testing. There's some complexity when you're writing tests too. So when you want to achieve code isolation and dependency management with K-unit, you end up having to introduce things like patches inside of the kernel, and I'll show some of that here in a minute on a later slide. But obviously you introduce those patches, and then all of a sudden you have to do the maintenance on those patches too. And that starts to scale up if you're doing, once again, if we go back to the last slide, we're talking about these highly detailed testing small isolated units and writing many tests. That maintenance burden starts to stack up quickly. Another disadvantage when you're writing tests with KUnit is that the write, execute, observe cycle is kind of slow because you have to boot and execute the kernel. And especially if you've got, oh, go ahead. Oh. Does someone have a question? Oh, go ahead. Oscar, do you have a question? No? Okay.
All good, so happy to welcome you. Good morning.
Okay, great. Where was I? Right, so yeah, so you have to, the write, execute, observe cycle. This can be slow because you have to boot up the kernel and get everything into the right context and conditions. So I'm on the next couple of slides after this slide. This is sort of an overview of what I'm going to talk about for the next couple slides. But this is a kind of a demo of a tightly coupled test where we're trying to minimize the dependencies so that we can test something very small and specific, right? And it's a bit of a toy example, but even this toy example, I think, demonstrates the difficulties pretty well. So a list of several of the things that you have to change to do this dependency management is you have to add a config item so that you can enable and disable your particular test, and then any of the mocking sort of functionality that you had to introduce. And by that I mean, because you can't do something where you can introduce a real stub or a mock, you actually have to do some, as part of the test framework, you have to do that manually, where you have to inject some defines into the code so that you can turn on and off certain items of functionality as part of your test. And I'll show that in a second. But you have to, and because of that functionality you have to turn on and off, you end up having to duplicate code for various data structures and add test data to check sequences of events and set up the preconditions for your test that you would normally have to, in a normal situation with KUnit, you would have to boot up the system and wait for that kind of condition to take place. If we're trying to introduce those conditions more artificially, then there's some manual code they have to do and maintain to do that. And then extensive additional calls are needed to set up data structures. Once again, due to that inability to do mocking. So here are some code samples. The first, these first two blocks are basically all of the duplicates of some of the code that you have to bring into your particular test. The area that I was doing this small example on was GPIO and testing something to do with the line rec function. So the line rec iactl function is. So you can see, I mean, this is once again a bunch of extra code that you have to bring into your test. Here's the test itself, and you can see in the middle here, there are several steps that you have to do to set everything up. Now, another option, so this is attempting to get sort of feature parity with the normal unit test environment, where you would be able to mock things out and test out of context. Normally in K-unit, you would often test in context where you're waiting for the system to get set up with the conditions that you need in a more normal flow through the code, right? Whereas this is actually sort of injecting some pieces of functionality. So it does make it more complicated here. And then these are all of the little config pieces and if-defs that I had to inject to make it work the way I wanted, right? To be able to check that a certain function was called in a certain way. So after you've gone through the effort of writing that test and the getting around the inadequacies that you run into, you have to build. So some things that you run into when building, once again in the context of these detailed tests where you might have many of them, you have to build the entire kernel every time because the tests are built into the kernel. And once you start to run into maybe greater than 1,000 tests, you start when you're doing really tight unit level tests, you're probably going to require even just from the kernel binary size, you're going to start to require multiple kernels to do all those tests. And that obviously has its own maintenance burden. And it makes it difficult for, what's the word? Fidelity, there we go. Fidelity with your actual kernel. So, you have a bunch of tests built into different versions of the kernel, and you're running into issues with test fidelity of the kernel actually resembling the real kernel. So you have high time expenditure for multiple builds, obviously, and then you have to maintain all of those. And if you're doing something really specific, you might have to maintain those patches yourself, and there's a high maintenance burden for that, obviously. I alluded to this earlier. When you're executing the test, you have a heavy dependency on system state, which is why I went to that whole exercise of writing that test earlier and attempting to extricate that dependence on that system state and the dependence on other pieces of the code from the specific code under test. If you have a lot of tests, once again, like we're talking about, you're going to require a whole lot of builds and a whole lot of boots. And especially because of different system states, you might have to boot more times than you actually have. Say you got 10 kernel builds with a bunch of tests each. You're still going to have to boot a whole lot more times than say that 10 because you have different state context based on what you're trying to test, and they might conflict with each other. Long execution times are a problem too, right? Once again, because you have to oftentimes wait for a particular system, the state to settle in a particular way before you can actually do the test. As opposed to conventional unit tests where it's you're only building and executing and testing the particular unit that's under test. You require at least emulation, if not real hardware. So you got to run on like QEMU or similar. And then because of all of those things, automation in the build pipeline is resource heavy, and that can stack up costs and time and everything else. So I ran a little demo of that one small, toy is not quite the right word for it, but very small constrained example where I eliminated those dependencies. So what I demoed, showed above. So basically, the end result is you have to turn on some config options, run the KUnit wrapper script, and it ended up taking, as you can see there, elapsed time 143 seconds, which for one very small test is considerable.
Add one other thing to that too.
Yeah, absolutely.
When you add code coverage instrumentation to your kernel, you have even
Yeah.
less room for
Yes.
in there, so it gets worse.
Yeah, absolutely. Yeah, and that's actually, it's good that you bring that up, because one reason you may need to go through this exercise of writing KUnit tests in this way, where you're striking some of those dependencies, is for code coverage specifically. So, yeah, I'm perfectly open for questions. I have some backup slide information too, but I realize I'm pointing out a lot of problems and not really any solutions here. So.
That's what this is for, right?
Yeah.
Not the problems and everybody start. Oh, sure. Sorry about that.
This is Mike. Wow. So this is not a question really, but so I'm Thomas from Google, working on the Chrome OS kernel, and we had a couple of people like play a little bit with KUnit as the way to like have tests that can be shared between upstream and like our internal test infrastructures. And one of the limitations that we found is that like you need to specify the stubs like explicitly in the code inside the function that you want to stub out. And so we did actually have a couple of approaches, like I think using kpro and stuff like sent to the mailing list. You might be already aware of those, but just wanted to know that it's probably far away from like, the mocking and faking that you mentioned, but it's the first step towards that, I guess. So
yeah.
Just wanted to mention that.
A step towards some workarounds, right?
Go ahead,
Oh,
David.
can't hear
If
you.
you've got a question. Yep. Nope, we can't hear you.
We see your mouth moving.
Yeah. Check for double muting. Type it in the chat. We can't hear you yet, so just type it in the chat and we'll go from there. While he's doing that, does anyone else have any questions they want to? Okay.
Well, I think it's important here to like group the problems into two areas, because not all of the problems you mentioned are specifically KUnit problems, but just problems of testing the kernel, like having hardware like that it's hard to get the preconditions right, and so that, I mean, it's not a problem of KUnit. It's
I'd push back on that a little bit, because when you're testing other code, non-kernel code, and you say you're using a more traditional unit test framework, that provides a toolbox that lets you set up those preconditions without having to run a whole bunch of dependent code, right? And I think that if you could do something similar in the context of the kernel, you could get around that. So I mean, I can go on my backup slides, but I actually threw together a prototype using a third-party unit test tool, and tested the same little section of functionality that I did with KUnit, and was able to do. I'll go to that slide actually. So was able to build outside of the context of the kernel. So basically what I did was isolated that section of code from the kernel and built it and ran it basically in user space or natively. Either or, I tried both. And you can use those tools from that toolbox to set up those dependencies and set up the state information the way that you want, without having to actually execute all that kernel code. I don't know if that answers what you were pointing out. But.
Well, I think it adds to it because you can improve. And I'm just saying there are some problems which are inherent if you want to test the kernel and not like in user space. If you're depending like on hardware reactions or whatever, I mean, you probably need reboot.
Okay, yeah, I mean, I see what you're saying. Even outside of those, hardware dependent scenarios, if we're just talking about, once again, isolating and testing small sections of code. Sorry, I'm distracted.
It's okay. I'll let you guys continue that. David has managed to type in his question.
Oh, okay.
And so he's saying, we've had a bunch of existing stubbing mocking features, i.e. static stubs, and 2 features that Thomas mentioned, which might help to some extent. Also, have you tried using the UML mode? It tends to build run much faster.
It does. Yeah, it does. I did try. It does build and run faster.
Yeah.
It doesn't solve a bunch of the other issues that I brought up about patches and maintaining many tests and all that. But yeah. So back to what you were saying. So what your point? Okay, so let me make sure that I'm understanding what you're saying. Your contention is that some of these issues I'm running into are inherent to testing the kernel as opposed to the tool itself. Okay, so specifically in the example that where I'd written this test, and I think many other examples would be like this, especially when you start talking about safety, verifying safety functionality and code coverage and those types of scenarios. The tools that you get in a normal unit test framework help you deal with those in a way that KUnit does not. That's what I'm contending, and it's what I actually was. Unfortunately, this forum isn't great for doing demos, but if you want to talk later, I can show you the demo that I did on using this third-party testing framework. I was able to a lot more easily isolate the code that I was trying to test and mock out the dependencies in the system state. And then, the execution times and everything else were a lot better with that as well. As I kind of listed the advantages that I was finding on here. And then, the last thing I did say is I think maybe the reason people haven't applied some of these other unit test types of tools and methodologies is because there is definitely some pain with getting it set up to actually build, right? Because mocking out those dependencies can be complicated because, well, the kernel is monolithic and very complicated. The particular tool that I chose to use incorporates a few open source bits, but one of them is CMock, and that does a bunch of automatic dependency mocking, and that actually helped greatly. So I didn't have to go and try to manually mock out 62 header files with all their associated functions and everything else. So there's a question back there.
We tried this about 20 years ago by pulling out the net filter code and running that in user space. And the difficulty there was that doing the mocks was like an order of magnitude more difficult than writing more tests.
Than just writing tests.
And KUnit has been a much more feasible approach than that was. It was a while ago, so like the infrastructure was very different then. But yeah, we certainly found the KUnit approach was much easier.
Yeah, and yeah, like I said, that was a long time ago. So some things might have changed, but yeah, I mean, I can understand that, especially with that the one demo I did. The initial setup was difficult, but it did end up being extensible. And I haven't played with it more. I kind of did an initial prototype. That's the nice thing about the particular framework that I grabbed is that I'm using is CMock. I don't know if you've heard of it, but it's all automatic, right? Those dependencies are automatic, and then if you need to actually stub something out, you can tack it on, right? I mean, in a lot of cases, most of the dependencies you have to mock out are indirect dependencies when you're building, and there's not really a lot you have to actually do with them. So you're limited to just the handful that you actually have to inject some kind of logic for checking something. Where it's opposed to KUnit, you have to, as I showed earlier, if you want to test something very specific that's internal to a function, especially like a static function, then there's a bunch of extra code you got to tack in to the kernel in various spots to get hooks into the information you need to examine. So
I use this technique from time to time, usually if I'm making a big change to a fairly isolated piece of code, all right? But the other experience I have, aside from the kernel version changes, is that if I'm, depending on what I'm changing, I make different choices from one time to the other about what I'm mocking. And so for me, it's been kind of a thing I do to test a complicated change. On the other hand, over the past 25 years, QEMU and KVM have got a lot faster to boot. Doesn't help with device drivers, but the overhead of dropping the kernel is much less than it once was.
Right.
Okay, and I guess we conclude, because we're at the end of the time for this session. Get into the next one. Yes. Tobias, you're up. And we have now 2 shorter sessions. So, and then after these 2 shorter ones, there's also explicit additional discussion slot added for Matt, Luigi, Tobias, so that we just get additional pulling time for the field of testing and requirements. So just give it a start. I'll give you 5 minutes warning.
Okay, so I'm on there. Hi, my name is Tobias Deming. I'm software engineer at Linutronics, and I'm also a contributor to the StrictDoc open source project. And in this talk, I will show you how it would look like if we realize the requirements definition process that we have seen yesterday and today from Chuck and Gabriel with StrictDoc. And disclaimer up front from StrictDoc perspective, we have already committed on the required functionality to realize what we need for Linux requirements in that regard, and have published this in the latest release. But of course, from the Linux perspective, this is different. There it's just a proposal that adds on another proposal, and in the end, it's totally fine if we end up with another tool or no tool at all. But the collaboration so far was fruitful, and I would like to continue. Okay. I will point you to our GitHub repository where we did a working demo of integrating Linux and StrictDoc. You can clone the repository, play around with it. It has GitHub CI integration to show all the automation steps required to build and validate the final requirements document. And then we will look at a simple example of if you as a kernel developer want to add a new requirement, how this would look like in practice, which text files would you have to edit, and what will have to be placed there. And then we zoom out a bit. I talk about the traceability model, because what we have right now is quite simple. We only have low-level requirements in the proposal and tests. This can be linked together. But actually, in such a technical documentation, you may have more items you want to represent. And let's look if this has value. And the other topics, I think this is more backup. We could do it in our discussion afterwards. Let's see. Some introduction to StrictDoc as a tool. It was created in 2019 by Stanislav Pankiewicz, who, by the way, is, I think, in the online audience. So, hi, Stan. And thanks for your strong support in the last weeks. And yeah, till then, it is continued to be developed by him and Marina Baljura as the main developers. It has found quite some traction, as you see from the statistics. And I think the core concept can be explained like this bold sentence here. Let's cut prose and code into atomic nodes, give them IDs and attributes, and link them together to form a graph. So this is different to how we used to make documentation with Sphinx, for example, where you have just documents which may have some meaning by convention, but you cannot build a graph with structured items of it. And yeah, this is good for traceability, of course, if you need to provide evidence to certification bodies, or from a developer's perspective, if you want to do divide and conquer, or if you want to challenge your own assumptions, then all this traceability helps a lot. We can do different input formats and different output formats. There's a native strict doc format, which is kind of a domain-specific language. We will see it in a minute. Yeah. Then this is the GitHub project I was talking about. And let's see what we are doing there. It's actually quite simple. So this is text processing, nothing more. StrictDoc will pass the Linux source files for this text that come from the Linux requirements proposal. And it will additionally parse so-called sidecar files. And when it finds entries that match on the ID, it merges them into one single node and on runtime. This happens when we call make HTML rex, which is just a small wrapper I did around StrictDoc, of course. StrictDoc will be called under the hood. And the outcome of this process is then something like this. This is a requirements document where we have all the parent nodes and child nodes just one click away. So we can go to the related source code from here. We can go to the related test code from here. We can, if we had, also go to related parent requirements, for example. And we also have different views. What we have seen before was a more linear document view with sections and subsections, but you can also switch to a more graph-like view where you see the parent-child relations behind the items in this technical documentation. And by the way, I think it's not really readable, but what we see in the red boxes here, these are custom validations. This can also be done. I added a custom validation that checks if every requirement in the graph has a related test case, and if not, flag a warning. That is what we see here. This is done through an StrictDoc API, so that you can hook in your own validation functions. Okay, now say you want to add a new requirement. And this is the most basic example I could think of. On the left, we see the trace events source code. We go to a function that is not yet annotated with requirements, and we add there a temporary ID and the requirements text. And in the side-by-side StrictDoc file, the sidecar, we add such a requirement stub, which is intended to carry metadata about the requirement. So we have a split here. The content shall stay close to the function, and metadata shall rather not pollute the source code and stay outside of it. That's the idea behind. Okay, and now this ID is only temporary. We need something that StrictDoc can relate these two things together initially, but then we will call next strict doc manage auto UID. And what this does is that it generates the stable ID and the hash ID. We heard of this before. The stable ID is just a random hash that never changes. And the hash ID is a hash over the project name, the source file name, the requirements text, and the function content, the function definition. Okay. And what this allows us to do is to detect changes in the code. If someone alters the code, then rerunning this command will give you a different hash sum, and you know something has changed. Now I wonder if this is the smartest way to do it as we implemented it, because we really calculate the hash byte-wise, and if someone does a white space change, then you already have a different hash sum, and this has no semantic meaning. So maybe we need to, it would be more convenient to have a semantic hashing here, like Cochinelle interprets the source code. Yeah, not yet there, just a comment.
About that, please consider that the code in the kernel doesn't change as a byte. I cannot submit a byte. Nobody will ever accept a white space after a line as a commit. So
yeah, I understand, but probably, I think there couldn't there be refactorings that have really no functional effect?
For the moment, this is.
I think you made a greater point, though. I mean, there are, spell check fixes, but that's not the norm. The norm is a functional change or a refactoring change. The other thing I would add is initially your stable ID and your hash key would be the same because they're calculated the same way. You want to avoid the need for any form of central coordination of ID generation. That idea is DOA. So initially you would just generate the hash and the stable ID using the same tool.
Yes, and by the way, we have to change that because, as I said, the stable ID is a random hash. This is not what you have proposed. We should, if I understand correctly, also there use the hash sum for.
Correct. Just generate the same way, and then the stable ID stays the same. It never changes. Hash key is what drifts.
Okay, but after doing this auto ID, we are almost there. We call strict doc export and see that our annotated requirement appears now in the new requirements document. We can commit this, send this to maintainers, and maintainers will have a diff view, which makes it probably more convenient to them to semantically check which requirement attributes have changed. And that's it about adding requirements. Now I have another comment about what do we actually want to trace. This is what we have now, requirement to test relation, but we have way more valuable items around. So how about, I did this with the example of timer create. How about adding LWN articles, for example, as parent user story? Because, well, in this particular example, the LWN article revealed that there is some CRIO checkpoint restore functionality that actually involves a flag in process control that leads to addition of a flag in the process control function, which then affects how timer create will behave. And you never know what the user story behind this if you don't read LWN or get to talk to Thomas in lunchtime, which is not actually traceability. Yeah, this would be one point. Can we assign LWN articles with an ID and link them. Another one is the POSIX specification is, in my opinion, also a good high-level parent requirement, a higher level specification, which affects how our Linux system call looks like. Okay, and then there still remains the question of how vendors would use this. I drafted this in these gray boxes. So vendors will have their own requirements, and how would they trace to our lower level requirements? I have no idea. Maybe you have. I think they will know. They will need some kind of high level requirement.
Well, the stable ID is for traceability into for anybody who would want to. So an OEM would absolutely have a higher level requirement tracing into the stable ID. But even if it's just kernel code nobody ever traces into, you still need some island of stability to form look back to.
Okay, and I think we are at the end. That's fine. That's roughly how far I wanted to go. Okay.
For you, maybe. Yeah.
Hello everyone. Sorry, I'm bad voice today. Even worse than Gabriele. So we stay at the same hotel. So the name of the presentation is Traceability as Code. Is a kind of proposal to move the traceability definition in a configuration file. And the talk is about so the idea in general that can be used by any tools that is working in that area, like also StrictDoc, but with a bit of, let's say, details on Basil that is implementing this idea for the first time, probably. So my name is Luigi, I work at Red Hat, and also member of the technical steering committee of Elisa, and I'm developing this tool that is named Basil. And so it's a kind of a flash talk, so we have just a quick overview of the tool and some focus of the idea. So the tool is a centralized web application that have a goal to, let's say, centralize most of the work that need to be done from quality engineering and functional safety expert to have in a collaborative environment. So it's a kind of multi-user web application that have some, let's say, key factors. So it comes with a user interface, REST API, and comes also with an embedded test infrastructures, but also have some plugins to interact with external test infrastructures like GitLab CI, GitHub Action, Testing Farm, that's a Red Hat project, and also kernel CI. And it's also able to export the traceability matrix in SPDX and to import-export work items in different way. And in the recent version, we also added support for in-app AI suggestions. So user can directly get suggestion from an AI model and simplify, let's say, the definition of the work items. The name comes from the integrity level we targeted at Red Hat for the automotive operating system we are developing. So it's not pizza, Italian pizza style. And it's actually developed under Elisa. So this is overview of how the tool is working. So essentially for a software component, you can specify a reference document that you can split in snippets, and you can define the traceability on each snippet of the reference document. The reference document can be anything, the source code, the specification, your manual, whatever. And that's a detail of the traceability that you can create on the snippet. You can have multiple level of requirements, test specification, test cases, test results. You can link bug fixes and bugs to your test results that can be executed from the tool itself. And you can also trace justification on any kind of documents to it. So why I come up with this idea? Because with Linux, we are talking about, say, a really big project, and not everything is in the same place. No, so we have a lot of, let's say, side projects that are big enough themselves, like ManPage project, Linux test project. Those are holding a great important piece of the puzzle. No, and so actually, I see they say the lack in traceability tools is about the ability to collect all those things together. So the idea is to have a configuration file where you can specify how you can read requirements that is written in any format, not tied to a single, let's say, constraint format for a single tool. From a particular repository, how you can read test cases from another repository, test results from a project like CKI from Red Hat or kernel CI, and how you can collect all those things together, and which format your traceability should have, how things are connected together. So what is the relationship behind all those things? Everything can be defined in a configuration file. That's the idea. And the idea is also to come up with a standard that can be used by anyone. So that's just, let's say, an initial work that is, by the way, available in ELISA Basil instance that is available online. I will give, I share the link later at the end of the last slide. So that's more or less the workflow. So work items are handled in the different Git repositories, but you can maintain a configuration file that holds all those information and the rules to extract the data. So that can track an evolving branch or a fixed commit, so depending on you. And so this tool is provided as a command line tool, so it's easy to integrate in a command line, in a pipeline. So you in a pipeline can generate each time the traceability matrix, and you can then later on export the SPDX SBOM of that traceability from using some CLI tool from Basil. And so each configuration is not tied to a single format. You can specify the format of each things. And it's also easy to extend to custom rules or to vendor projects. So if you have requirements in a vendor tool, like, I don't know, the famous ones, so that are providing anyway interface to interact with them. So let's see how this workflow looks like. So you can specify the software component that you want to work on. So a list of API, essentially. And then you can specify for those API where the reference document is defined, where is the repository. And from that reference document, you can extract the snippets that are defined in your configuration file. And later on, you can specify the list of work items. For each one, you can specify the repository and the rules for extract each information. And also you have the work items defined. You can also refactor the value and generate the traceability. So let me go through some implementation detail inside Basil. So this is how looks like a piece of configuration file for defining a repository. So it's written in YAML, so you can leverage anchors to simplify the configuration file. And you can specify the URL, the branch, and then you can filter across the repository, selecting in which folder you want to look, in which file you want to look. And you can also filter the files with files that are containing some informations or not. So for example, in the case of some kernel API, you can specify where the API is defined, and you would like to see a file containing the implementation of that API. So after that, you have some, let's say, work items. For example, just thinking about requirements, you have in Bazel requirements have two fields, just a title and a description. But in general, for any fields, you need to define rules to extract a piece of information from a text file. And that in Bazel is done using definition for where I have to start looking at the information and where I have to end to look at. But it's also possible to create relational search. So you can say, look for this implementation function and then look for this comment that is on top of the function, stuff like that. So, and you can also explode the result in multiple elements, just splitting it in some ways. Those are a few of the possibilities, but all the details are in the documentation of the project. So let's see details of how it's possible to extract, for example, some software requirements. So we identify some work items candidate, looking at a particular repository, and for we defined rules to define the title of the requirements using, for example, some magic variable that essentially have, so during this iteration, the tool is providing some magic variable like the current iteration, the name of the API you are working on, the repository path, a lot of the information that you have available during the analysis. So in this example, we are generating some requirements with defining some, let's say, constant for the title. And we have, let's say, a more complex definition for the description, as we saw, let's say, the same example of before. After we identify all the possible candidates, we can also filter over the candidates, because we can define rules to skip some candidates that no fit our, let's say, search, that can be done using contains, no contain, or regular expressions as a filter. And we can also refactor the results with some common let's say, rules like regex substitutions, trim, or adding prefix or suffix, like that. So this is an example on how that apply to the suggestion from Elisa, that at least the one that we had so far, because it's kind of evolving things. So in the same example, so at the end, to extract all the requirements from this, let's say, proposal, we just need this piece of configuration file that can be maintained somewhere in the kernel, for example. And that's for requirement, but we can specify something similar for test cases and for test results, for example. And so essentially, we look for a particular file in the Linux kernel. We search the file that is containing the function definition, and we look for the first definition of the function expectation inside the comment. And starting from that, we split all the elements with, let's say, the bullet list that is defined. So in that way, we are creating all the requirements. So, and this is explaining, in how in the configuration file you can directly define the nesting and the relationship. So you can have a definition for your software requirements, and inside that you can define other requirements. If you have high level, low level, mid level, whatever architecture or let's say, hierarchy defined. And then you can specify other elements like test specification, test cases, test results, whatever, everything in a configuration file. So that's really, let's say, a draft. Let's take it as a draft. And really, so the idea is to come up with, let's say, a more robust and shareable standard that can be itself a project that we can use in all the tools. So no matter which tool you want to use for traceability, you will, let's say, leverage the same concept behind it. So this is how the Bazel tool looks like, how you have a web interface where you can configure your configuration file, you can edit it, and then you can directly execute it from the tool. It will generate your item inside the tool. This is the URL of ELISA instance of Bazel. You can join the tool, creating your own account. Just take in mind that when you join the account, there are different user roles, and for each user there are granular permissions. So the owner of a work can decide who can read, who can write things. So when you join the instance, an administrator need to promote your user. So it's normal if the first day you cannot do anything. It's normal. So just wait until the admin will promote your user, and then you can play with it if you want to use the live instance of ELISA. And from that, you can also create your requirements, test cases. You can also run your test on a Fedora virtual machine directly from the ELISA instance. So that's all from my side. I have some stickers to remind you about the project here, if you want to take, if you have any questions.
There's not a direct question. I would say we can also open, because we saw Tobias' part, Matt's part on like K-unit testing, improvement, then the traceability for the test cases along with the discussion about the specification. So we have built up the time that we have a buffer and can keep the discussion. So you want to get started?
This looks like a really good tool, but the thing that keeps striking me is he's laughing, so he knows what I'm going to say. On your previous slides, you talk about line contains, and then you have the name of presumably part of a function, then an open brace. Now, I know in the kernel we always put the brace right next to the name, but there could be one or more spaces in between. There also could be functions that end in that don't necessarily, like that's not a full function name necessarily. I've used and written tools like this before, and that approach falls down very quickly because humans are writing code that we're trying I think there needs to be some sort of, and regular expressions are not sufficient. There needs to be some sort of way of semantically asking for something that's there. Merely looking for patterns is not a good approach. It makes the maintenance of this extremely difficult, unfortunately, just because you could end up with another thing in there that has the word API, or I can't see a good example here, but line contains star context, and then there could be something immediately after it. There could be more than one line there. So I guess what I'm trying to say is there needs to be a better way of anchoring things rather than line contains.
Sure, yeah. Line contains is just one of the possibilities. So you guess also you can use regular expression, but as you said, probably it's not enough. But it's a good point to.
Regexes get long fast, and I've in order to solve these kinds of problems, I've had to write regexes that are 2, 3, 4 lines long.
But the point here, but I totally agree with you. But the point here is just it's not a solution. No, what I want to say is that that's an idea to move the traceability definition somewhere else, not inside one tool. No. I mean, we can find a way to solve that technical issue, because at the end, so everything can be doable, no, in software.
Well, I mean, that's why, we can talk about using like the SPDX rec ID that we're developing in the template. We've still got a long road to go. But that's one. The canonical form of solving the problem that you're talking about is you got to use the abstract syntax AST directly and look at the symbol. And then of course, those never get aliased or anything like that. So that's not, that's not,
Semantic reasoning.
It's really hard. Yeah.
No, I know it's hard.
Yeah.
The problem is if you don't do it that way, it gets harder.
Correct. And that's why like templating using the tag template format that we're trying to work on might actually be a better, because you can just zoom right in on those.
Sure.
Yeah.
That's really good.
Yeah, fair.
You can also have the same function defined multiple times in the same file. So I mean, that's
a comment here. In StrictDoc, we are using treesitter to parse the C files, and then can know from the concrete syntax tree where a function starts and ends and what is the line range. And I'm not sure, but if I understood the intention of use of Bazel correctly, it might be a solution. Let, for example, StrictDoc do the source code parsing, let it use treesitter, then we don't have this regex problem, and let it create some SPDX compatible output, and Bazel might pick up that SPDX compatible output. Is this one way to go?
Yeah, I mean, Bazel is already able to import SPDX requirements. So requirements defined in SPDX. So the tool itself is working, let's say, from a user interface that you can write your own requirements from the tool. Is not the only way to play with the tool. This is kind of new approach, but the idea is not, let's say, let's do that way. Is as a multiple people working on different tool requirements, traceability tools. So why we, instead of having our own way to say, you have your StrictDoc file that is quite unique, so only your tool is able to create and read this file, this format. So, I mean, instead of tying to a particular format, the idea is to come up with something, let's say, more abstract.
That's also the reason why I added SPDX to the tags. I wanted to have like sort of a neutral, no particular industry or anything, and SPDX is already in the kernel too, so it's understood what that meant. So keying off of those tags, and then wherever they're deficient, let's work on that in the template. I mean, it is very, very draft, and that's why we're bringing it out and talking about it at these conferences here, to even open source some in North America and Europe, trying to see where that goes. But that would give you something you can automatically key off of. It's just a known entity.
Yeah, but probably directly. So I mean, probably the tool as it is will work with all the SPDX definition already, because are simple. No?
Correct.
So it's easy to play with that instead of the C code. Yeah. So it's yeah. So let's see. We also have, let's say, a technical discussion that is around. I mean, all the not only the traceability tools, but also the items that we need to manage in the repository. So as I understood from last conversation, so the idea from Elisa should be to propose a new patch set without all the SPDX things in the source code and move everything in the sidecar. And probably we can, let's say, agree on that with other Elisa members, and then try to come up with another, let's say, round of proposal also from toolings.
Okay. Any further remark, suggestion? If not, then we are at the end, I guess. This was the last part of the Safe Systems microconference. Thanks all for participating in active discussions. And I think just to recap, we had quite some various type of topics. Maybe some would also fall in testing MC or so, but yeah, I hope that we get a chance to take this discussion further, especially on like what can be a way of identifying respective snippets in the code, how to get the link to the testing. Then we have a more traceability way to make it more robust, sustainable, reliable for the next 10, 20, 30 years. Because we will have new people coming on, and it's good to have meaningful documentation in whatever kind of form and way of testing, especially with a lot of regulations coming up where you need to comply to security practices internationally. So therefore, it can be valuable to add these kind of things. And we hope to find a low to no impact way for maintainers so that it's adds benefit and not an extra effort or hurdle. Thank you so much.
You get a group photo with Lisa folks?
Oh, yeah.
Commemorate the
Oh, she's in a. She got something from.
This is the crazy picture.
Always on the side of that. There is an intrinsic self. Too wide.
Hello, hello, hello. Oh. Nice. Can you hear me? Also from the streaming? Someone can write maybe on Matrix. Oh. Hello. Hello. Eric Mutama, he's here. Eric Mutama. I don't know if it's the right pronunciation, but what? So Eric Mutama didn't upload the presentation yet, so it would be nice if he upload his own presentation. And also Louis Chamberlain. Where is Louis Chamberlain here? No? Okay. So yeah, 2 sessions without presentation. That's not. Yeah. So it's okay if I take a photo as the Steve Rosted style. It's okay. So we are left like 3 minutes from the start. And because I added that faster introduction when I thought maybe it's not necessary and I removed, but now I'm a bit regretting to have removed the introduction of current testing and dependability, at least for welcome everyone. So thank you for coming to this MC, and I hope that you enjoy the session. And this the style of this micro conference is by 10 minutes of presentation, and we will try to have like 10 minutes of discussion, but it's not strict. A bit strict, but not super. At least 20 minutes are strict. And yeah, we have some speaker gift. I don't know if I say, but yeah, we have like free speaker gift. And because we choose by votation, I think it's fair to give the gift to the first free presentation. And so I will also not get a speaker gift. And yeah, I think we are almost at the time. So maybe if Thomas is starting to prepare for his own presentation on WAPI testing with KUnit. And so, thank you and welcome everybody. So I am currently uploading all the presentation that we have. So enjoy your presentation.
Thank you. So let's try this. Test. Nice. How do I get back to my presentation? Something happened. Ah, nice. Okay. Okay. Should I?
Is on?
I think so.
Hello.
Let's test. Okay. Hi, everybody. I'm Thomas Weistrow. I work at Linotronics. And today I want to present you something I did to make testing for myself easier. And I hope somebody else also gets some use out of it. So, where I'm coming from. So, I started working on the VDSO and the kernel some time ago. What the VDSO is not really important, just that there is a special user space API between the kernel and user space. I was migrating a bunch of architecture-specific code to some generic framework, which means, or which I always want to test what I do, which means I need to test the kernel on various architectures, with like 7 architectures in total. And I'm iterating, the patch series had like 30 patches, and I need to test every single patch against the self-tests that we already had for the VDSO. So we had these self-tests, I wanted to use them. They were written by the experts who originally wrote the VDSO, so it's good to reuse as much as possible. And why K-self-tests? The K-self-test framework has support for cross-compilation. There is, after you have your cross-compiled executable, the steps to actually execute this executable and get the results back are left as an exercise to the reader. This is my interpretation of this exercise. So I tried to get a test setup that was easily automatable, that was runnable with a single command, and it worked for all the architectures. I'm the maintainer in the kernel for a subsystem that is called LPC, and we have our own test rig, which allows us to run a small user space, a small test program against various architectures. So I took the existing VDSO self-test and transplanted it weirdly into this test framework, and that worked. But it's completely unmaintainable and not upstreamable in any way. So, but it worked. So this was the basic for that, more or less. So then I thought, what could we do to optimize all of this? So we have KUnit, which provides an easy way to run or to have a test configuration as part of the kernel tree, to maintain it, to build the tests, to run the tests, to get a result back from the tests, even for different architectures, to run it on QEMU, to send it to a real device. We all have this in KUnit already. So how can we leverage all of this? So how can we create the glue? So we have in the kernel build system the concept of the user proc. A user proc is a user space application compiled, so it runs on the target kernel. So if you're cross-compiling, it will give you a target executable. And that works, it's already maintained, it's already mainline. Nice, we can use it. So now we have to actually get this thing into the kernel. A normal case self-test expects you to have a real root file system with a shell, with some utilities and everything. But this is all stuff I need to get from somewhere. If I want to build a test for Spark 32, I need to get a Spark 32 distribution. And then I have, I don't know, S390X, and I need an S390X distribution. And there may be no distribution that has all the architectures. So I'm mixing and matching stuff, which is a lot of work. So the idea was, the kernel can already execute executables. So we embed this test binary that I built as a user proc directly into the kernel. Like a random object, we embed all kinds of objects. The VDSOS itself is built as a library and embedded into the kernel as a blob. And we have many other examples that work like that. And then we run this executable as part of KUnit. So we get the scaffolding we are used from KUnit and we apply it to this test executable. But now if you run a blank executable for an existing K-self-test, the K-self-test may run into issues because it expects to run from a regular file system, which has a dev mounted, which is proc mounted, and all kinds of other stuff. So in addition, there's a pre-init executable, which prepares the environment for the test executable to run in. And then we have the output we want to see because we want to know if the test failed or not. We have TAP. K-self-test already emit TAP, which is a standard format, and KUnit has KTAP, which is a slightly different standard format, but in the same structure. And wouldn't it be nice if you could just combine all of it because it was designed to be combined in general, and then we get a unified reporting out of that. So in the end, the goal is to have everything work as a regular KUnit test, all the tooling, all the commands should work as is, but we get it for K-self-tests. Yes. One small excursion. So we're building this user proc. For user proc, normally we do libc. So if you build a kernel, you get like a Clang is a cross compiler, it compiles all the architecture, but it does not contain a libc. So if you're on an x86 machine, you build an executable with Clang, it will use the libc from the system. But if you build an S390 executable, it will not work because it's missing the libc. And now libc is the project I'm working on, so the synergy is kind of, I'm not unbiased. So, but the thing is, no libc is in libc. So it's maintained as part of the kernel tree. It's header only. So whatever architecture you're compiling for, the libc is built together with the application and you have a completely self-contained application. And it's not moving, it's moving in lockstep with the kernel. So if something breaks, all kernel developers know exactly what to do, where to report the bugs, and we can backport the fixes and whatever it's needed to get it working again. And it's regular kernel code, regular kernel development process. But no libc is limited. So there are some changes that are needed to the K-self-test. But in the end, it turned out all the changes that were necessary are small cleanups or stuff that was useful anyways. So I've mainlined many of these fixes already. And I never mentioned that I needed for this specific use case. I just said the existing stuff is broken. Let's make it better. And they all went in. How big it is it? Right now it's like 400 lines of code for the implementation, so it's really not much. The whole goal behind this is to glue the existing things we have and that are maintained and documented and integrated with the rest of the ecosystem, just glue them together so we have something that works for this use case too. The K-self-tests right now are maintained completely in a completely dedicated directory. It's in tools testing K-self-tests. They have their own build system. They're not using K-build. But on the other hand, a kernel developer is already accustomed to using K-build to build their code because this is what's used for the kernel. So we need to integrate these a bit. What happens, or what I used, is a wrapper. So we have a source file for each user space application that just includes the kselftest source file, and then everything works as is. You also need to define a new make rule, or you make variables to get the special compiler flags you get from kselftest. So there's some duplication there, but hopefully most tests don't need that. Then there's a special macro that will embed the compiled binary into the object file. Then there's a module that is created, or you can also link it in as a built-in module, and the build binary is linked into that module. You get some kconfig symbols to define your new test unit test, the same as you would do with a non-UAPI KUnit test. And you get a nice KUnit config, like it's also done normally. How does it look? Very boring, the same as every other unit test too. We have a KUnit config in libvideos or tests. We give an architecture and the test fee to run, and we get an output. It takes 1.5 seconds to run. To build it on my machine, it takes around 1 minute to build it completely from scratch. So there's not much overhead. All the build dependency tracking that we have from kbuild is working completely fine. It's just one command go and it works. So here's not much to see, but that was the point behind it. So what is happening, or what has happened so far? So I mainlined my original VDSO patches with this using these tests, and they worked, and stuff has been mainlined for some time. For that it worked. It found various bugs in the self-tests themselves, because nobody ever ran these self-tests on some of the esoteric architectures. And then I tried it and it broke. So I fixed these too. I'm also doing other stuff in the VDSO, so I'm still using these patches. Every time I do something, I merge my test branch into it and use it. And my colleague Nam, he has another subsystem, and we also used it for that one to validate that some kernel invariants are kept. So there are already external users that are interested in that. What's the problem so far? So there are some discussions on the mailing list. There was no real uptake. I posted this some months ago, and there was no real demand from external users to have it. There was some demand from my colleague. There was some demand from the UML people for their self-tests, because when I run some self-tests against the UML kernel, they just failed because stuff was not implemented. So nobody ever bothered to implement these things for UML properly. If it gets merged, how does it coexist with tool testing self-tests? Do we keep the duplication? Should one be deprecated at some point? What's going to happen? One thing is, this framework really is only for single test executables. That is one executable, it runs completely standalone. It does not use any shell scripting around it. It's not multiple binaries doing something together. It's only for very simple self-tests. So it's probably not going to ever be a full replacement for tools testing self-tests. How do we handle libgcc dependencies? Some architectures, they are missing, for example, multiplication for 64-bit integers. For that, we have libgcc, which provides wrappers. But libgcc is also not available because our cross-compiler is missing libgcc because it doesn't need it. Do we need to have our own kernel libgcc? It's not clear yet. So different architectures have different ABIs or UAPIs. For example, we have x86-64. The native ABI is x86-64. So far, so good. But we also have 32-bit and x32 ABIs. So they can be supported, but it's additional complexity. Is it worth it? Is it not? I don't know. What to do about these complex test programs? We could embed more complicated test binaries into the kernel, but then the kernel gets bigger and maybe it's not worth it anyways. It's not really a unit test anymore. This is some of the feedback I got on LKML. Does it matter? What is a unit test anyways? I'm not sure. Yes. So that is some links about, there was an article on LWN, and I have my submission to LKML. And now I think we can start the discussions.
Got it. So the question is, well, KUnit is unit tests, of course.
Yes.
So When I originally envisioned this, I thought it would be something like we would be booting up KUnit UML kernel, have it somehow have K-self-tests, just run them, meaning as user programs. You're already in the kernel mode. So you would do that. Why not take that approach? Then you would not have all of these issues.
But to run it, K-self-test, I need a shell.
Well, I mean, K-self-tests can be built, right? You need to build them.
Yeah,
You
but-
could kick off the build from KUnit.py script.
Yes, but to run the KUnit framework, to run the K-self-test framework, I need a shell, I need some...
Yeah, you would need those. You would
and
need those.
I don't have these.
Yeah, you don't have all of those.
For
Okay.
example, their architecture, there is no official distribution. You can get the distribution image from some random Chinese GitHub repository, but...
Well, I mean, okay. So if you have any even close to BusyBox level of
Yes.
infrastructure or environment, then you can do it. So you're saying you probably do not even have the...
Yes, I have nothing. The framework I have right now does not require anything more than we already have. We already have a compiler because we're building the kernel, obviously. We have a libc inside the source tree, and that's it. There's no external dependency whatsoever.
Okay, so you will have to do lots of, in most of the K-self-tests or multiple binaries in some very often. And they are driven by the scripts.
Yeah, but these binaries, they don't depend on each other. You can
Right, correct.
And this works. The VDSO things also are like 2 or 3. So this completely works. Just each one is executed serially in its own dedicated namespace where it can't see each other. But if it works as this, it works fine.
Okay. So where is the bloat coming from then?
This was the feedback. Because essentially, if you build a kernel with all the tests, you suddenly have a lot of stuff inside the kernel, but that's the case in any way.
Well, I mean, I don't know. Did you measure the bloat? I mean...
Well, you get the binary.
Yeah.
It's like 3K for regular binary, but you can just build it as a module. So then it's a module and you can load it or not load it, and it's your problem.
Exactly. So, okay. I need to play with that and see. I haven't had any chance to do it.
So I wanted to make sure I understood why we have this like strong constraint on dependencies. Is it literally just that like these architectures like don't have BusyBox, or is it more like?
I think the mic is something.
Oh, is it?
I can hear you, but I'm not sure if anybody else can hear or on the stream. Maybe take it closer.
Oh, what? Oh, yeah. Okay. It's just right. So I wanted to understand better what the reasons are for these constraints on dependencies. Is it really that the architectures don't have BusyBox support, or is it more to do with like, oh, well, we need to form the consensus on like how we get those dependencies, how we build them, like what, like we need to pick a build system and a distro and a blah, blah, blah.
Yes, you would need to figure this all out on your own every time.
But I mean, could we in tree like have some equivalent of a Nix flake or a BusyBox definition or something that like not BusyBox, I mean build root, that like fetches these dependencies, like I guess there are some set of like shells and things and libcs that are simple enough that they can be built for any architecture, or is that?
Do that, but then you would have like new tooling again. You need to install build root, and maybe it doesn't work. Then you have a new test driver because KUnit won't be able to drive this. Because you can use the KUnit.py tool right now, and you could extend the KUnit.py tool, but KUnit does not depend on this tool. You can build your test kernel, you can ship it off to your hardware however you want, and get some result back, and this with this scheme it will work. So I also had some test kernels for some recent issue, or some test machine I got, and I built this test kernel, I sent it off to the machine and got back the result without having to mess around with NFS root or something else, or cross compilation.
Yeah, like, just to be clear, I'm not saying that like this being able to have shells, etc., is something to do instead of what you've talked about, because there's clearly advantages. But I'm wondering if if like the next step would be to get those advantages while also allowing, like, imagine if we could run all of the like KVM self-tests without needing a distro, right? That'd be amazing.
Yes,
what would
for
it
the
take?
shell, I would say try to not use a shell in this case.
But I mean, there's already a whole body of tests written
Yes,
in
that is
Bash, right? And it'd be nice if we could run those without.
So you will probably need some sort of adaptation anyways if you use the no-libc stuff, because it's limited and you may need to adapt your tests a bit or extend no-libc. It would depend on your specific use case, how it works.
I like the idea quite a bit. I really like the Python test runner that we have for KUnit today. Like, that is such a great experience as a developer. You write your test, you use the runner, it builds the kernel, it launches QEMU, it gives you the answer. It's fantastic. It's such a time saver. And I'm really happy to see that you're trying to integrate that efficient workflow into testing that can be done, like, that has to be done from user space.
Yes. I also, at one point for the VDSO stuff, I got a bug report. Yeah, like in the Fedora build system, it broke. And like, okay, great. Now I spent 2 days to figure out what it's actually doing. And in the end, I had it down to one invocation of KUnit.py. And the change was if it's 64K page size or not. And it's so easy to reproduce. You have the command, you execute it, bam, result done.
Yeah, I mean, that's exactly it. Like I know some of the K-self tests I've already got and written will run perfectly fine in this framework. And they'll match nicely with the kernel-based K-self tests that are already, or the K-units that are already in the subsystem. And from like a maintainer perspective, being able to run one command to run all of my tests is such a time saver. It is such a pain to get the K-self test to run inside a testing VM in a scripted, automated way. Like, we don't have a tool that does that.
Exactly, that would be the idea. I think I have the output somewhere here. So these are the actual files I wrote for the VDSO stuff. We have a, this is the scaffolding. I just wanted to have the output, the raw output. Do we have it?
We are starting to get out of time. Sorry.
Sorry. Okay. Yeah.
I just wanted, assuming my sound's working this time, that I wanted to say thank you, because not only is this really neat, but also the various fixes you've put into everything, very, very nice. A lot of other things have improved as a result. My general thought on this is it's a little bit ugly squeezing entire binaries into, you know, the kernel in order to run things, but it's so useful in practice. I find myself not worrying nearly as much about it having used it as I did before I used it. So I have absolutely no objection to it going forward. My thought is maybe this is a good indication that extending the KUnit tooling should help to other test frameworks might be a way forward, or to more deliberately support user space things.
Mm-hmm.
We are out of time. Sorry.
Thank you.
Thank you. Thank you, Thomas. Yes.
Hello. Before I begin, I'm leaving a box of typical Christmas pastries from Spain. So help yourselves. Watch out with the allergens. If you don't like the talk, at least you got free treats.
We are a bit strict on time now. Sorry. So enjoy your talk.
Thank you all for coming. All right, running kernel space tests from user space. Main idea in the first slide, that's something that everyone told you to do. So there you go. I think from here on, we can go straight to the discussion section, but well, let's see if we can go through the rest of the deck first.
So can I ask you a question?
Let's wait until at least the third or fourth.
I know, but I am going to ask the question anyways. because we went from converting, we used to have a way to run user kernel space tests as modules, loading them as modules to run them in K-self-test. So we moved away from that when KUnit came along. We actively converted a bunch of tests into KUnit. So now are we, I mean, it's just a question as you start the discussion. Are you proposing going back to introducing something like that in K-self-test?
I find some good use for it, yeah.
You'll have to justify that, I think, because we did a bunch of conversions. But let's go see what you have.
Okay. Another good news is that they also tell you that this talk should be not about something you did, but just present a problem and let the discussion happen. Good news is that I didn't really do anything, so I can go ahead. Okay. The main idea is to provide a kernel feature and an interface to extend the reach and capabilities of user space tests. And you would say, why do we want to do this? Well, Thomas already did something similar. You can see your work link there. So genius minds think alike. The main purpose would be to try to bridge the gap between the kernel space test and user space test. The way I see it, these two types of tests are fundamentally different in some aspects. KUnit tests, for instance, are supposed to test very specific parts of the kernel code paths and call specific kernel functions. And they're supposed to run under predictable conditions mostly. User space tests, on the other hand, are supposed to test functional behaviors, and they target kernel interfaces, but not specifically kernel functions or code paths. So the feature I want to talk about would try to remove some of the restrictions of user space tests and try to enhance the flexibility of them. So in order to do this, I wrote a very simple proof of concept, like the simplest possible implementation and interface that I could think of. Forget about the name. I know it's overly generic. It's just a placeholder. So focus on the idea rather than the name. So we do have a feature that's compiled conditionally with an additional, with a new config flag. So typically this would be disabled by default in a production kernel. So we will have no space overhead and no danger of exposing parts of the kernel through yet another interface. We will have the core of the functionality would be a k-test object that basically defines a function to test, a name for it, and the size of the parameter buffer that it needs. And then a framework that would provide some basic functionalities in the kernel side to register kernel functions as tests, and in the user space part for listing the current registered tests and running them, checking the results, etc. So the interface could be as simple as that, a user-face interface with 4 endpoints. One of them to list the currently registered tests with the name and the size of the parameters they require. So there we have a couple of tests that don't require any parameters, and another one that requires 4 bytes of a buffer with the parameter contents. We will have an endpoint to trigger one of the tests by writing the name of the test, and optionally the address of the buffer containing the parameter data, and a couple of endpoints to check if the test ran correctly, if it's still running or if it ended, and the result. So defining a test would be in the kernel side as simple as that. It's just a function, regular kernel function, but with a specific signature. It returns an exit code, and it takes an address to a buffer containing the parameter contents. So in the second example, there's a function that defines the parameters with a certain structure. And then again, in the kernel side, that's a possible way to register them using a function like k-test register, where we would say, I want to use this function. I want to register this as a test with this name and the size in bytes of the parameter buffers. Then in the user space side, this is how it would be used from a case of test, which is pretty trivial. We would have a set of helper functions, could be a part of the case of test common library. So we will have a function, well, this will take care of handling this SFS interface for you and do all the sanity checks and all that. So we could have a function to check if the test exists and retrieve the size of the parameter buffer required, another one to run it, another one to check the result, so on and so forth. Okay, since I'm running out of time, I'm going to be fast. So running the case of test would be like just running a regular sub-test. The difference is that now we had access to specific kernel functions explicitly. So back to the reasons why. One of the reasons that I told before was that the case of tests aren't supposed to run with predictable conditions in the kernel. They may run at any time. So a way to mitigate that would be to provide a kernel function that sets certain conditions in the kernel that we need in order to start the test, register that function as a k-test, and then call that in the case of test as a test fixture, so we can prepare the test environment before we run the rest of the test. Another reason that we saw was to extend the flexibility of case of test. So now we are not limited to run to test only the provided typical user space interfaces like system calls, sockets, ioctls, etc. We can now trigger specific functions that are published in a controlled way. Of course, this can be misused and exploited and all that, but remember, this is meant to be used only for testing, so don't do that. Be a good person. And also, I think this could help encourage with certain things about, well, the adoption and standardization of test code in the kernel. There's providing a framework like this or something similar or a feature like this would be a way to keep test code as part of the drivers, as part of the core code in a kernel tree, just as KUnit. And I think it will foster good practices, making the test code more explicit, since it would live together with the kernel code and driver code, etc. And as pointing to what Sheila said, I think this would eliminate the need to keep out-of-tree modules that currently live in case of test directories, and that could be incorporated back into the kernel and keep in sync. Well, it will be more explicit that they should be kept in sync with the test code itself. So now you can hate me and ask me everything you can. Please, easy questions preferred.
So what you're describing, why can't you do this with KUnit? Because essentially KUnit would, you could set KUnit has data files, right? Metadata files. So you could, first of all, let me ask you a different question. Do you envision these as a unit tests of the kernel or open box? You're kind of integrating open box with closed box tests. Is this a unit test?
No, I would keep unit. I wouldn't treat these as unit tests. I believe they serve fundamentally different purposes. My idea with this is something that I figured out was missing, and maybe I'm wrong, is that there's no reason for user space tests not to be extended to be able to incorporate some of the functionalities in KUnit tests. But that doesn't mean that I think it's a good idea to turn case of tests into KUnit tests. For me, they are different. The purposes are different, and I wouldn't try to mix both. This is just a way to, even if it's just to, as I said, to incorporate a way to create a set of known preconditions before a test inside the kernel. So this is a way to use user space tests not only with the interfaces provided by the kernel, but by entering directly and running specific kernel functions.
But okay, but could you do that with either eBPF or like, as a gross abuse of KUnit, make a KUnit test that does that, and then just call that prior to the K self-test.
Most likely.
Relatedly, check out the K-fuzz test talk and K-fuzz test support, as that does a very similar thing. As that patch series does let you inject code from externally. There also has been discussion. KUnit has parameterized tests. There's been talk about ways of using maybe some of the K-fuzz test stuff to inject parameters from user space. So at the very least, K-fuzz test is prior art for the technical way of implementing this. More likely, maybe it's something you'd want to integrate more directly with and have a common framework for.
Thank you.
I have a question. In the second or third page, you said have the new kernel config value for the config key test is already enabled in the stable kernel. Yes, for the key test. It's already enabled in the...
None of this is integrated.
Yeah, we ask a question because we already use the... we already test the key self-test, and but we test into the direction folder and so prepare the testing. So if this value enabled in the stable kernel, that's it's easy for us to run the key self-test, and we can update our test framework to trigger it. I think this configuration is very useful for the feature testing.
Okay.
Okay, thanks.
So something like this. So the setup of your test environment, you can do this with the framework I just proposed, because it's driven by KUnit. You can execute whatever kernel code you want before you're running a user space test, and then clean up afterwards.
Mm-hmm. Okay.
Yes, I think it's a good idea to look into existing ones. I just came from the K-fuzz test. I was looking at what David said, and then also look at, you can do, I agree with Thomas, that you can do stuff with KUnit, existing KUnit. I would not go the direction you are going. I would not want to see K registers coming in. It sounds almost like ioctls and that kind of data passing. It will lead to a lot of security-like issues. So we wouldn't want that. I do want you to take a look. I mean, I think this is a good idea. I think you want to be able to set up, what you're saying is maybe if you want to test a system call, for example, you want to have the system in a state first before you test. Perfectly reasonable idea. But I think you want to use KUnit existing in stuff instead of introducing something new.
Okay.
That's what I would say.
Yeah. There's a question back there.
So I think there are a few K self-tests where the K self-tests K-build magic has a way now to say, I'm a K self-test, but I come with this module.
Yeah.
And it's somehow integrated into K-config in a way I don't really understand.
Yeah. This is one of the things I mentioned that...
At the beginning, yeah.
Right, yeah.
So like that's something that I find quite, like I've got a couple of tests that I've never bothered to upstream because it's like, we in Google anyway, because it's like they are a user space program and a like sketchy module that does something sketchy to like, so for example, there's one in the Google kernel tree that like does a bunch of pathologically arranged page allocations so that you can run your tests in a like worst case memory scenario. Mm-hmm. And I've got a benchmark where it's like I load a module that just directly exposes the page allocator API to user space so that I can exercise it in evil ways. And my first thought when you started talking about this was like, oh, this is like a standardized way to do that kind of thing.
Exactly, yeah.
But now I'm thinking about the fact that this new K self-test system exists, which I've just admitted I don't understand, but maybe, extending and improving that new case self-testing is a like smaller step forward that you could take?
Yeah, probably, yeah. Should take a look into that. Okay. We're ahead of time, I can't believe it. Any more questions? I think we can wrap it up. Thanks a lot.
So next we have Etam Graham with Fast Test. Welcome to Etam.
Hello, can you hear me? Yeah, cool. All right, so I'm going to be talking to you all about K-Fuzz Test today. So for a little bit of context, this was originally developed at Google, but I'm continuing to maintain this independently now as I try to get it upstream. So I'll assume that most of you probably know about syscaller and sysbot. And these tools have been incredibly effective at all right, thank you. Yeah, so sysbot and syscaller have been incredibly effective at finding bugs in the kernel from broad system call fuzzing. I think it's over 13,000 as of today. But these fuzz from the system call interface, and many critical kernel functions are very difficult to effectively exercise from there. So these include things like parsers, format converters, new code being added to the kernel, and unit testing is great, and you can target individual functions with this, but it lacks the discovery power of a strong coverage guided fuzzer. So this leaves a bit of a gap in the testing ecosystem, something we might want to fill. So our goal here is to make it trivially easy to fuzz individual functions within the kernel. We want the solution to integrate with existing fuzzing infrastructure, such as syscaller, but we also want it to be agnostic so that you can bring your own fuzzer if you wish to. And in the long term, we want to help find and prevent bugs within the kernel. So let's look at how K-Fuzz Test is doing this right now. So I'm going to illustrate this through an example. So let's say that we want to fuzz the following function. Now, this is a real function in the kernel. It's doing some pretty complex parsing. This is a PKCS7 format. And it's taking this data len pair. This is a very common sort of structure that you see in kernel interfaces. And this is all that you need to write in order to fuzz it with K-Fuzz Test. This is, 4 lines. And for most cases, this is all you're ever going to need to write if you want to start fuzzing these types of functions. In the general case, if you want to be representing more complex data, like structures, nested structures, multiple pointers, you can use the general fuzz test syntax over here. Now, this is a macro-based API. I'll leave it on screen for a little while, but the main point that I want to make here is that it's familiar. It looks similar to what you might write for a user space fuzz target or a unit test. And something in particular that I want to bring your attention to here is the constraints and annotation system that's implemented by K-Fuzz Test in the API. So unlike system calls that kind of have to be resilient to untrusted inputs, like calling write or something with garbage input should never crash the kernel, internal functions have more of a contract. You can't be throwing null pointers into random functions and expect it not to crash. So you need a way to express this. So this is done with the expect and the annotate macros, which are very similar but have a pretty subtle difference. So an expect or constraint is something that you can check very easily at runtime. In this case, we're just checking that the pointer is not null. Annotations are a little bit different because these are things that you can't safely check at runtime. For example, here we're expressing that the data field of the struct that is being passed as input, this is quite similar to what was presented by Ricardo actually with the parameters that are being passed in. We're saying here that it's an array and not a single element. And we're saying that the data len field is the length of data, because if you start passing around an invalid length, you might do needless out-of-bounds accesses that will crash the kernel when it's not a problem with the function, it's a problem with your input. So at a high level, this is kind of what kfuzztest looks like. It's debugfs interface, so pretty much exactly what Ricardo was presenting before. And this is currently under upstream review. The idea is that you write your inputs into a debugfs file and it'll invoke the fuzz target. VM Linux, when compiled with dwarf information, contains all the metadata about the fuzz targets, the domain constraints, the annotations, built right in. So the idea is that a fuzzer can read through this and basically understand the shape of the input that the fuzz target is expecting ahead of time and not generate invalid inputs. Invoking a fuzz target looks a little bit like this. It's pretty much the same thing, except here there's a serialization step. This is important because we want to be able to represent this structured data in such a way that we can write this into the kernel directly. So there is some serialization required. So now I'm going to go over just a usage example of how we can use kfuzztest. So what we're going to do is inject a bug into a real function. This is the same function that I showed you guys before, the pkcs7 pass message function. And we're just injecting a +1 here. The data length is invalid. So the idea is we want to trigger a ksan report. We compile the kernel with ksan. We want to see a nasty stack trace at the end of it because it's accessed an invalid byte. Now, you might think this is a pretty easy bug to catch when you're reading through the code. It's pretty straightforward. It's just a +1. You'd absolutely catch that. I argue that this isn't so easy. This is where it is. I don't think anybody is able to spot the bug. It's right there. And it's calling into an even bigger function that has hundreds of lines of code. This is not really easy to catch. It might be very time consuming. You might not catch it at all. Now, kfuzztest catches in about 30 seconds when syscaller is fuzzing this target. And this is not running on a heavy machine. This is just on my laptop. Spin up syscaller, fuzz the target, and you get this nice ksan report that leads you right to where the overflow happened. Now, kfuzztest isn't perfect, so I'm going to go over a point of contention that has come up in the mailing list discussion. The big thing is the serialization complexity. Now, kfuzztest does rely on a serialization format, a custom serialization format to express complex data. So it includes pointer-pointee relationships, but also has nice properties like being able to sandbox all the pointers. You can't just point to arbitrary kernel memory. You guarantee the point within the inputs. You're pointing at something valid. There's a lot of plumbing that you need in your fuzzer to be able to serialize such inputs. So for example, for a simple data-len pair, you end up with something that looks like this. So there's like 2 metadata regions before we even start the data. There's ksan red zones so that you can detect out-of-bounds accesses. So most of what you see here is not even the actual data that we want to fuzz with. It's just metadata. So this was the main reason for implementing the fuzztest simple macro that I presented a little bit before. Is it also exposes a simplified interface so that you can just write a blob into the file instead of having to serialize anything. And the goal here is to lower the barrier for entry for new fuzzers. Now, let's speak about what kfuzztest is today. So it's currently under review. It's in its third iteration on the patch series. There were 2 RFCs before this. And there's general interest. Kind of the common, or the sentiment is that more tests is not a bad thing. It's a good thing. We want the kernel to be well tested. And ultimately, we're hoping to get some more fuzz targets upstream. So as I mentioned before, I was fuzzing this target with syscaller. Now, the reason for this is that syscaller has had kfuzztest support out of the box now since around September. It's natively supported. If anybody has used syscaller before, you'll know that you have to write descriptions for your system calls to describe what the inputs are meant to look like. A cool thing about kfuzztest is since all the constraints, annotations, and fuzz targets are embedded in the VM Linux metadata, you can just, that's all done automatically by syscaller. You don't have to write any descriptions there. The long-term goal here is to continuously fuzz these targets to find bugs in the long term. There's also a support for a local fuzzing program. It's basically syscaller light. You just copy it onto a VM or any machine and just fuzz using the same powerful fuzzing engine, but without any orchestration. As for other fuzzers, there is some tooling support here. There is a bridge tool that's also under review at the moment. It's basically turning blobs like devu random into structured inputs. It works well for basically, transforming random data into something that kfuzztest recognizes as a valid input, but it does require you to write it's a pretty simple DSL, but you still have to write a DSL basically describing the shape of the input before you can actually fuzz with this. So there is a little bit of extra work needed there. As for the fuzztest simple macro, since it does support this simplified interface, you can pretty easily support fuzzing it with something like LLVM fuzz1 input, which is just, libfuzzer. And I was playing around with it. It works pretty well, but then you have to implement KCOV collection, etc. So this is something that I consider to be out of scope, but you can fuzz it pretty easily without having to implement a serializer. And yeah, that's all from me. Thank you all for listening.
Okay, so could you elaborate on the serializer part? What exactly are you doing in when you do that?
What do you mean exactly?
Why is it? What are you actually doing? You're actually injecting data, injecting. Is that why you need the serialization? Why do you need? Why do you need serialization?
So kind of the idea is, let's say you have a structure that takes a pointer or multiple pointers. You can't just copy the struct as it is into the kernel because it's got user space pointers contained within it, right? So you have to relocate all the data associated to an input into the kernel. So you already need some metadata there to basically say, okay, well, this pointer that is a user space pointer should actually point to a kernel address that I don't know yet, right? So this is why we flatten everything into a single buffer. We have other stuff, like for example, this region array you see there. It's a metadata region that basically says how big is every logical region, which is like a piece of data being pointed to. And we insert some padding between each of these regions so that we can poison them, so that if you access within these regions, it'll trigger a KSN report. So yeah, basically the serialization is needed for relocation plus some extra added stuff to ensure that the framework is effective. I think there was a question at the back.
There's a question in the back. Pass it.
Thank you for a great talk. And I'm wondering about, so my understanding is that we will be able to forge specific function using the debugfs interface. And there will be some user space tools like cgcolor that we'll use and maybe provide some more superpowers like cgcolor that providing us the reproducers and some more informative logs. But I personally don't want to use that much of user space tool, but hope to be able to do the forging test only with the kernel source tree. Will you provide some kind of lightweight user space tool inside kernel tree that will be sufficient enough for simple forging use cases?
Yeah, so this is what the bridge tool is for. Where did I speak about this? Here. Yeah, so the idea with the bridge tool was to make something that kind of uses smoke testing, right? So you can take just some random source, like here I use this example devu random, but any blob that you can think of as in a file, and then send that into a kfuzztest target with serialization. So it's kind of like just a tool for performing the serialization for you, and that was designed to try and lower the barrier for entry a little bit as well. So yeah, this is in the kernel tree. This is going to be in the kernel tree, right? It's under review.
but it will not provide some kind of very reachful things like reproducer generation. Right?
There aren't any plans for that now. I think the main reason for this is that it ends up being a lot of code trying to commit into the kernel at once. It ends up being a lot of stuff just for supporting kfuzz tests, and trying to keep it as minimal as possible in that regard for now. Didn't want to do anything too complex. We're kind of offloading that to user space tooling.
Thank you.
I suspect that maybe with Coccinelle, you could probably automate the generation of the target fuzzers that you need. So therefore, you don't actually need the code in tree. And then you basically have a grammar that basically just parses existing routines that have a specific format. And it's just basically an just a target that generates the fuzzing. So therefore, you may be able to get pull off not having a lot of extra code upstream as well.
I mean, yeah, that makes sense. I mean, look, the fuzz tests themselves are pretty easy to write. I think an experiment that I did a while back was just like getting a bunch of kernel functions in a JSON and getting an LLM to write fuzz targets for it, and it works pretty well. You can automate this, but you could even do it more.
Yeah, I think with Coccinelle, you'll probably be able to get better determinism for accuracy for that. Because LLMs, are loose, right?
But I guess the difference is that now if you auto-generate it, you can target entire sources, right? You don't have to write it by, source at a time. You just automate it.
Yeah.
Parse the entire thing.
That's an interesting idea. Thank you. I don't think there are any more questions.
Is this kfuzz test like results? You have something that your like Syscaller have the Syscaller dashboard for showing result?
For kfuzz tests, like Syscaller dashboard for it? No, not yet. Since it's not currently merged. I mean, the Syscaller support is implemented in the sense that the targets can be fuzzed. There's no sysbot support for this. That's something that maybe could be done at some point once kfuzz test is merged, but not yet.
You were saying that you was at first playing with LLVM and fuzz for checking like configuration files on the kernel by writing structure for kfuzz test to making the anyway. So why you're using the fuzz test simple?
I'm not sure I understand the question.
Yeah, you have a fuzz test simple that is a simplified interface.
Yes.
So how is it simplified? Like we are calling.
Yeah, it's simplified in the sense that it's for the data length pairs, right? So it's for that type of interface. This is pretty common. We made a special case for it. And this allows you just to write a blob. You don't have to serialize anything. You just write it as it is. And
I see.
Yeah, it simplifies having to write any kind of serializer. Currently, Syscaller is the only code base that supports serialization for it because, I was working on both aspects together. So there was no need to implement it for any other fuzzer.
I see. Thank you.
Thank you for great work, Heban. I'm curious about how we can take some strategy using the kfuzz test when we wanted to specific fuzzing some module or core subsystem. Do you recommend some way of some kfuzz test usage that a good way? Yeah.
Like a good way to use kfuzz test?
Yeah.
I mean, I guess find your favorite function and then just write a fuzz test for it. I mean, it's pretty straightforward. I guess you can just play around with it, find stuff that looks interesting to you. I guess the main thing, my main goal with kfuzz test is to make it super, super easy to use. So if you try using it and it isn't easy to use, then let me know and we can work on that.
Thank you.
So just a side note that fuzz tests by design are supposed to live in the tree along with the code so that they can be continuously fuzzed with Syscaller. So in the case something regresses, yeah, we can detect that.
That sense, how much intrusive is that code? I understand it's pretty much isolated from the rest of the sources as a standalone file, or am I wrong? How much like interferes with the rest of the sources like that you are trying to fuzz?
It's in isolated files.
Yes, right.
Yeah. The suggestion was to put it under like subsystem/tests, as that's currently what's done with KUnit. So we're trying to stick with the same sort of principles as we use there.
If the API changes, then you have to also change the fuzz testing file, or if you have
Yeah.
it generated, of course, you don't. Right?
And that is exactly what I'm saying. Grammar, use coccinal here. Then this doesn't have to be, dealt with. It'll be dealt with automatically.
I mean, yeah, it does make sense. I mean, I haven't really thought about the trade-offs of doing so, but it does totally make sense. So, yeah. All right, I don't think there are any more questions. Thank you.
Thank you for your talk. So next we have Sikso's practical KVM fuzzing of Alexander Potapenko. Thank you.
So, hi everyone. My name is Alexander Potapenko. Today I'm going to talk about a project dedicated to improving KVM coverage fuzzing and about SysOS. So fuzzing KVM requires valid state on both the host and the guest side. On the host or level 0, the setup requires running sequences of KVM ioctls, and getting any of them wrong can render the whole VM useless. The bigger challenge has always been the guest side, or level 1, which also requires executing meaningful code to trigger VM exits from level 1 to level 0. Previously, we relied on 2 strategies to do that. Both of those hit a wall at some point. So first, we had hard-coded assembly blobs that we installed into the guest into the guest address space. These worked to some extent, but they were rigid because the fuzzer couldn't mutate those instructions to find some edge cases. So the second strategy was, in addition to normal assembly instructions, the fuzzer could also generate so-called pseudo instructions, which were like assembly macros. The problem here was that these instructions, once generated, were lowered into bytes, and then further fuzzer mutations could ruin them, which is basically what happened. That's why, yeah, it was suboptimal. So to begin with, to fuzz KVM effectively, we had to first reduce its massive search space, because feeding random garbage data to the hypervisor usually results in immediate errors. We had to rework the existing syscall descriptions, do some tweaks like replacing opaque black box structs with more precise structs, use some special no squash attribute to prevent certain mutations, provide constants instead of random integers, etc. The goal was to explicitly tell the fuzzer that which parts of the data are not supposed to be mutated, preventing it from wasting time on unsuccessful mutations. So for the host side, we leverage the so-called pseudosys calls. Instead of making the fuzzer guess a complex sequence of ioctls that leads to successful VM setup, we wrap them into the stable C function which guarantees a valid bootable VM every time we run, allowing the fuzzer to focus more on mutating the guest behavior. While pseudosys calls aren't new to syscaller, they actually existed in the initial version of KVM fuzzing. We made a critical architectural change, decoupling the VM setup from vCPU setup. They used to belong together into one pseudosys call. By separating them, we allow a single VM to support more than one virtual CPU, which is essential for race condition fuzzing. Now for the guest side, we had to come up with something new, which is SysOS. SysOS is an immutable C binary that runs inside the level 1 guest. Instead of generating raw assembly commands, we generate a sequence of API commands that SysOS interprets. This is crucial because it allows the fuzzer to mutate the arguments, like for example, which MSRs are being read or written, which values are sent to the port without breaking the instruction logic. So we expose different primitives for L1 operations, like executing some code, running CPU ID, accessing MSRs on x86, for example, handling interrupts and stuff like that. So on x86, we also extended this API to support nested virtualization. In this case, SysOS acts as a lightweight L1 hypervisor that abstracts away the architectural differences between Intel VMX and AMD SVM. There is a set of commands to handle the full L2 virtual machine management, like enable nesting virtualization, create VMs, execution commands to launch the VM and resume, mutation commands to flip the bits in the state in the VMCS or the VMCB, depending on the architecture. These primitives allow the fuzzer to trigger different interactions between L2 and L1. There is some ARM64 specifics. I'm gonna skip that. Just believe me, there is a lot of interesting stuff going there, but ARM is less mature at this point. Let me clarify our execution model. So unlike the standard VMM, like QEMU, for example, which runs in an infinite loop, a syscaller program is just a linear sequence of system calls. So we effectively unroll the run loop of the virtual machine into a discrete set of KVM run calls. The critical component here is the uexit command, which SysOS can use to yield back to the host. It's used to pause the guest execution to let the host run different system calls, like unmap stuff or change the registers right in the middle of the guest execution. Standard syscaller concurrency also supports marking certain syscalls as async, which helps us provoke some data races. So let's quickly walk through a real execution trace to see how this works in practice. So on the right, let me see if I can get the pointer. Oh, yeah. So on the right-hand side of this slide, this is a simplified syscaller program. This code runs on the host and talks directly to the kernel under test. The first few lines, they correspond to the standard setup. They open the KVM device, they create the VM, they set up the address space. Then the interesting part happens here in syskvm add vCPU. It contains a structured chain of SysOS commands that the fuzzer generates before executing the program. And these commands are then passed down to the guest. So in this example, you can see that first we enable the nested virtualization, then we create a VM, we load some code, these are just two instructions, halt and invd. Then we launch the virtual machine. We write something into the control block, and then we resume. So when the host eventually calls the kvm run ioctl, SysOS wakes up and starts interpreting the commands that it received from the host. So it starts with creating the enabling nested, creating the VM, installing the code, and doing VM launch. After that, it spawns the L2 virtual machine, which starts executing the instructions. Remember these two. And because the first instruction is halt, it immediately stops, traps back to the L1. And L1 just handles gracefully this halt instruction and executes the uexit to pass it over to the host. So at this point, the host may intervene and do something interesting to the VM state because it just received the control back. But in this case, the fuzzer chose to issue yet another kvm run call. So SysOS resumes here and executes two more commands, which are, one of them disables the halting by writing some bit in the control structure. And then it calls the VM resume, passing the control back to this second level of virtual machine. Because it's still on the halt instruction, it traps back, but L1 doesn't handle this because we disabled handling the halt instruction. It traps back into the host. After that, the host issues yet another kvm run, which lets SysOS pass the second instruction invd, which again traps into L1 and is gracefully handled by SysOS and passed over to the host. So this hopefully demonstrates the power of our approach, where we have very fine-grained turn-based control over the entire nested lifecycle. So we can trap, we can mutate state, we can resume with precision that was simply impossible when we just generated random blobs of instructions. So does SysOS actually help fuzzing? Oh, okay. Fine. Yeah, I'm almost done. So we attempted to validate whether SysOS helps fuzzing or not. So we managed to find 9 bugs in KVM that use SysOS reproducers, which sort of demonstrates it. We've also found a number of standard KVM bugs that were discovered as a collateral damage when we were reworking the API descriptions. The stronger validation comes from the fuzzer itself. So we noticed that the genetic algorithm is actively selecting SysOS programs. Their share in the corpus gradually grows. So hundreds of these programs are successfully triggering the nested virtualization, proving that the fuzzer wants to use the API. And there is some quantitative proof. We saw immediate 5% jump in coverage when we rolled out the ARM64 prototype of SysOS. When we started fuzzing on bare metal x86, we almost doubled the KVM coverage. So this is particularly thanks to the newly unlocked nested virtualization, but also different parts of the of KVM got more coverage thanks to that. So there are some future plans here, but yeah, I'm happy to take any questions.
So can you talk a bit of the roadmap for the future?
So yeah, the roadmap is as follows. We want to support deeper nesting. So The most interesting part is running SysOS under SysOS, like in level 2, so that it can create even deeper nested virtual machines. We also need better ARM support, like page tables, nested virtualization as well, devices probably. We still don't support non-64-bit guest modes on x86, which was possible with the legacy KVM fuzzing, for example, the 16-bit or the 32-bit address spaces. It would be also nice to analyze the coverage gaps today and see how this could be improved.
I have a question for some page table support that ARM, the most of distribution like RHEL have a 3 type of the page size: 4K, 16K, 64K byte. So I run some running a test with the CZ color, and we can choose some other page type for the guest. So I'm curious about the CZ can support some when we take some different page size with on the guest with the host. Yeah.
Well, it's not implemented yet, but as far as I remember, KVM allows doing that. So yeah, this is totally possible. There is a small caveat that these SysOS is also distributed as part of every C reproducer that we send to KVM, and that C reproducer is usually compiled in the 64-bit mode. There might be some complications related to that, but I don't think so. Yeah, so it should work.
Thank you.
It's a fairly basic question. What sort of rate of cycles do you get with this?
Sorry?
Sort of how many iterations per second or seconds per iteration, or?
So when fuzzing on a bare metal host like a server machine, we get to maybe 100 per second.
Yeah, I was just thinking on the ARM support. It's probably parallel. It probably has similar things in x86 actually, but we have a lot of implicit traps to the hypervisor from the guest. So things like, if you execute certain instructions, or if you're doing floating point and we're doing lazy switch, or if you switch instruction set, or things like that, right? So it's not a syscall interface. It's not a hypercall interface. It's not a do a page fault. It's almost like you would want SysOS to do random instruction sequencing, but in certain parts of the architecture. And I wondered if you've looked into any support for that.
So am I getting it right that there are some implicit traps that cannot be triggered from the guest, or how do they actually happen?
I guess what I mean is, rather than, for example, having a hypercall interface, which is one interesting thing to fuzz.
Yep.
You might have, like the mem copy instruction might trap to the hypervisor in certain situations, but it's all implicit based on the environment that the guest is in.
Well, but still, there is some way to trigger it, like without doing a mem copy. Say there are the SMC instructions, right?
Mm-hmm.
You can just call them. So basically anything that could be triggered with a single, with an assembly instruction, we could put into SysOS and export as another command.
Yeah, so I guess the mem copy is an interesting one because there's a special context switch piece of code that runs in the hypervisor in response to that in some situations, and it'd be nice to get coverage of that. Is what I'm saying.
I see.
So I think ideally you'd want SysOS to have a way to sort of, certain parts of the architecture to tickle that part as much as it could with random instruction sequences or something like that, but maybe targeted towards trying to trigger these traps. I'm not quite sure how it would work, but
Well, we still do support random instructions, so it's now just part of the SysOS.
okay. So you do have support for that in?
Yeah. So it's a separate command that says, please run these random instructions.
Okay. So maybe if we could configure that to target certain parts of the instruction set, to bias itself to those, the instructions that trap, for example, that might be interesting.
Yeah, probably.
I mean, I would definitely be interested in that. So.
So I guess that's it. Thank you.
Thank you for your talk. And now, if I remember correctly, we have 40 minutes of break because I think there is coffee outside in maybe in 10 minutes. Where will be like something to eat. And yes.
That's the next question, right? What is Yeah,
speaker will have trouble.
Added to the end that nobody knows.
Hello. Louis Chamberlain is here? Okay. Can you please convert the PPT-X to PDF? Thank you. Hello, and welcome back to testing MC. It is now time, I think, of starting. And I welcome Alexander Nogic to give his talk. Yes. You can start.
One, two, three. Yeah, perfect. Okay. So, hello, everyone. I think it's time for one more Sysbot and Syscaller talk today. My name is Alexander Nagih. I'm a software engineer at Google, and I will be talking about continuous patch series fuzzing that's been given a name Sysbot CI. So after a brief introduction to the problem area, I will explain how it's been done on Sysbot. Then we'll share some details about the pilot deployment and some first results that we see. Okay. Yeah, I guess by now we have seen this multiple times today, but just in case, Syscaller is a coverage-guided kernel fuzzer, and Sysbot is a continuous system that polls, builds, fuzzes multiple kernel trees and aggregates their reports. Since 2017, Sysbot has reported more than 13,500 bugs to the kernel mailing lists. It's important to note that all these bugs were found when fuzzing tips of the kernel trees. That is, after the problematic series have been picked up by the maintainers, and sometimes even later than that. The average, the median bug discovery time on Sysbot is around 50 days. Apart from the personal experience and the common knowledge about what makes can make bug fixing easier, we have accumulated some informative statistics on Sysbot over the years of operation. Firstly, we observed that knowing the commit that introduced the problem is actually important for the probability that the bug will be fixed. So in our case, the reports caused by section attached were addressed 2 times more often than reports without it. And secondly, it's also important how after the bug was introduced, it was discovered. The probability is the highest when we discover it almost immediately, and then it gradually decreases over time. So the idea is to shift kernel fuzzing as much left as we can to address more kernel bugs with less overall effort. The overall approach is demonstrated on this slide. So for each patch series that is published on the kernel mailing lists, we perform auto triage. That is, we try to determine the base kernel tree on which it should be applied, and we try to determine the subsystem affected by the patch. Then we perform directed fuzzing of the patch series, focusing on the code areas that were modified by the patch. Then we must verify that the findings are actually introduced by the patch series, and then we send an email with findings under the original email thread where the patch series was published. And the objective is to do all that in the window between the patch series is published and before it's taken by the maintainer. So the first step is to determine the base tree and the base branch on which to apply the patch. The approach currently taken by Sysbot CI is to rely on the mailing lists CC'd by the patch author. We maintain a mapping from mailing list to the tree, to the kernel tree, and to the subsystem name. Then among the trees that match, we select the ones where patch series applies cleanly. Unfortunately, the reality is more complicated than that. So there is a tag that's supposed to help in such cases. It's called base commit. Unfortunately, only a minority of patch series actually included. There is a subject line, patch subject line, where quite often there's an indication of the tree where the patch should go. However, it does happen that the series actually does not apply there. Sometimes patch series depend on other not yet merged patch series. Sometimes they're based off quite old commits and no longer apply to tips of the kernel, to tips of those kernel trees where they were supposed to be applied. And lastly, some series apply cleanly, but still the kernel fails to build because of the incompatibilities elsewhere. So overall, we observe that these problems affect roughly 13% of the patch series that we process. However, it seems that these are actually the important patch series that we would have loved to fuzz. Okay, once we have base and the patched kernel, we can do the actual fuzzing. Unlike the regular Sysbot fuzzing, we use a slightly different seed selection mechanism with more focus on seeds that exercise the modified kernel code regions. Also, we can use the subsystem information from the auto triage step to reduce the set of the enabled syscalls to further focus the fuzzer on the important parts of the kernel. And we take corpuses from Sysbot not to start fuzzing from scratch each time. Even though such fuzzing is performed on the patched kernel, not all findings will be brand new. The kernel has numerous existing issues, so we must filter them out. The approach taken by Sysbot CI is to first find a reproducer for these bugs. Then we run this reproducer on the base kernel. If the base kernel crashes, well, we assume the bug has already been there. If it doesn't crash even after several attempts, it must be new and it can be reported. The system has been implemented and recently deployed. It's available, its web dashboard is available at the ci.sysbot.org address. On this slide, you can see a screenshot of that web dashboard. There you can see the list of patch series extracted from the mailing lists and their current status. You can filter them. You can click on the patch series title and get some more information about it. So it's currently not monitoring everything. There's only a subset of mailing lists that we take patch series from. We're going to extend it over time. And here's some preliminary statistics that we have accumulated between August and early December this year. So we have processed around 7,000 batch series. Among them, for 1,000 or 13%, we could not determine the base tree to apply them to, so we had to skip it. For 41%, the changes from this patch series did not affect the files that are included by the sysbot config, even though it's big, it includes lots of stuff, but the kernel is huge. So there is no reason to fuzz this on sysbot. And among the other ones, 10% we started fuzzing, but syscaller could not reach the modified region. So there was also no reason to continue. And 37% we actually did fuzz for full 3 hours. Since among these, we have reported 105 findings to mailing lists. So yeah, the main challenges or the main factors affecting the performance of such systems are as follows. So fuzzing is not and was never meant to produce deterministic results. However, we can work on improving the ability to focus it on specific parts of the code. Among the false negative cases that have been debugging, the frequent reason for them is actually not being able to find the base tree. And the current approach apparently needs further improvement. Because as I mentioned, apparently there is some correlation between the complexity of the patch series and the difficulty of finding the right base kernel for it. Also, the current approach demands that there must be a reproducer for every finding, which has historically been challenging for syscaller. And it's important to note that during patch fuzzing, we can only cover as much as syscaller tool can cover, which is a lot, but not 100%. So the apparent next major direction of work is to address those challenges, at least to the reasonable extent. However, even the existing deployment can be extended to cover other use cases and to process more patch series. I would love to hear your opinion on the following matters. So should we consider running more test utilities on incoming patch series? Should we maybe consider covering LTS backport candidates? And the idea that has been briefly discussed today during BOF, we could also try to shift it even more left and offer on-demand fuzzing of not yet published patch series. For example, if they are sent to sysbot's mailing list and not to the other public mailing list, it can take them, fuzz them, and report back the results.
It'll be cool if you fuzz the LTS RCs.
Yeah, so that was everything I wanted to share. I would love to hear your comments, ideas, suggestions.
I was wondering if you could say more about the focused fuzzing. So for example, if the patch only affected a particular IOCTL, is the focused fuzzing able to determine that and only fuzz that ioctl, or is it just fuzzing the entire file system if it's, say, a Btrfs patch? I'm just sort of curious, how focused are you making the fuzzing? Because when you said focus fuzzing, that sounded really interesting.
Yeah, thank you for the question. So the way it works currently is, at the beginning, we run the whole corpus we currently have on sysbot. We collect coverage from for every corpus program, and we observe which of these programs, the coverage of which of these programs actually goes through the functions that have been modified by the patch. So if some particular ioctl has been modified by the patch, it should be able to determine the function names that whose object code has changed between the base and the patched kernel, and then during the actual fuzzing, it will very strongly prefer the seed programs that did trigger that code.
So that must be a lot of data. You have coverage data for every single syspot potential reproducer or program, right? That's a lot.
But that's actually the normal mode of operation of Syslbot. It's for every corpus program that's in the corpus, it keeps the information about what parts of the kernel it touches. So we have this information.
I have a question. You mentioned that there's a certain amount of patches that we cannot, apply cleanly. Would it make sense to kind of actually fuzz changes that already landed on kernel next before they actually are released to, the next kernel release? And so we still get enough lead time before the next kernel release happens, but we already have these patches applied.
In a way, it's already done by Syslbot because it doesn't fuzz by regular Syslbot fuzzing, because it does not fuzz just the Torvalds tree, but also Linux Next tree. So if something is merged that really breaks stuff, it's usually discovered more or less fast.
Right. Yeah. But then we could also incorporate this mechanism of targeted or focused fuzzing on top of that, and basically kind of make it more effective in finding things. I don't know, I'm just maybe to ask from the different perspective. Is there that much of an advantage, fuzzing the actual patches on the mailing list before they are merged? To just picking the commits from the next tree.
The ultimate objective is to increase the chances that these findings are addressed.
Right.
And the moment before the patch is even merged is the moment where we can have the highest impact by reporting an issue.
I see. Yeah, okay. I got it. Thanks.
But the idea you mentioned that we can probably be more smart about Linux Next fuzzing by incentivizing the fuzzer to focus more on the parts of the kernel that changed recently. It's a good idea. And we'll probably also need to do something like that if we incorporate it into LTS patch fuzzing, not by considering each patch separately, but by looking at the diff between the LTS kernel releases.
Yeah, actually, this related comment. I know that some kernel subsystems have their own CI, infrastructures. I think the Linux Media does. I suppose this approach could also be so they very often actually apply the patches just to get them run through the CI. So actually, this could be one of the additional steps that those subsystem CIs could actually incorporate. And then I guess that would solve the patch application problem because the maintainers have to do that anyway. So a pair 3, Syslbot CI basically. The maintainers already applied them and pushed that to the CI, and then your thing just runs there.
It would be actually very interesting to hear from kernel maintainers who do have similar CIs for them, because unfortunately the kernel is quite fragmented in this.
Yeah, exactly.
But yeah, there are some things. Maybe these are from maintainers.
I am one such maintainer. Yeah, it does sound in principle interesting. Anything I'm CIing will be in a Git tree that I have on kernel.org. So if you're trolling them, you might find them find what I've done anyway. I would have, if I was doing it myself, I'd have to consider my compute, the compute resources I have to test things. But yeah, that sounds interesting.
If there are any more tests we can run on these patches, it's something we can definitely consider on our side.
Still related to testing, let's say, subsystem-specific trees, and the NetDev subsystem that is networking, we create local trees for running the CI every 3 hours. So patches received from the mailing list are collected in burst, applied to the base tree. We run the CI over it. And the periodic cadence, I think, could fit nicely with running fuzzers on top of this specific tree. Integration could be simple because the tree is somewhat already exposed. I think it would be very interesting for us to have this kind of pretest running.
If you already have functionality that extracts the patch series and applies them to the base tree, and it's already pushed in some publicly available tree, that would be very interesting.
Yeah, it's already there.
Then we should, I think, continue on offline.
Yeah. Okay. Thank you.
So Scholar is sending data to kernel CI, I think.
Yes.
And this data is sent to kernel CI.
Sorry?
Also, the data of the fuzzing is now sent to kernel CI.
For patch fuzzing, we do not, because as far as I understand, at kernel CI side, there is no similar functionality yet. And
Because
they
I
focus
think-
on fuzzing tips of the
Okay.
trees, right? So we can't send bugs for not yet merged patches.
Okay. I just thought that would be nice to collaborate on.
Yeah.
A way of showing some things on kernel CI dashboard, and having some way to have not have to look like. I see the syscaller, the dashboard that you told, but I didn't know about that. Usually, I just look kernel CI dashboard, so I thought was. Okay. So thank you. I think we are also out of time.
Yeah, thank you.
Hello. Next is Eric Mutama. Is here with us. Eric Mutama is online. So could you share your screen or? Yeah, but I cannot see him in the presentation person. There is Guillermo, David, but there is no Eric. So okay. So, okay. So we will go on with the next one, and then when Eric will go back, we will do his. So next one is Luis Chamberlain. So thank you.
We have 10 minutes instead. Hello, everyone. I'm Louis Chamberlain, and I'm going to be giving this talk with my colleague Daniel Gomez. We're at Samsung, and this is about how the singularities here for testing and our advances with generative AI on KDevOps. So KDevOps is a Linux distribution agnostic test automation solution, but it's also a development automation solution. Who here has used it? Just one person, okay. So KDevOps consists essentially of kconfig, Ansible, CI integration. We have an automatic dashboard. But if you're doing kernel testing, you'll quickly realize that essentially you cannot use Docker containers. So essentially, you need full virtualization or a cloud solution. And then for this reason, we have GuestFS for local virtualization. We also have different cloud providers that we support. Recently, due to the boom of AI, obviously, we have now Neo Cloud support as well. That's a cheap way to basically just use GPUs. We also support bare metal, and we are essentially working with the philosophy of automation and scalability. KDevOps at its core is a kernel automation framework for Linux kernel developers by kernel developers. It supports a series of typical workflows that if you're doing or file system development or block layer testing, that's essentially what you get. And over the years, this has expanded. We have started to expand on the tests that we support this year. The things that are in blue are the new workflows that we've added this year. And this has all been done and added using generative AI. We also have expanded the amount of tests that we support also to include AI workflows like BLLM, MinIO Warp, and BLLM production stack. That essentially allows you to do KV cache testing, for instance. So we also have now a proposed plugin architecture that allows you to add custom workflows or proprietary workflows. So if you are interested in leveraging the power of KDevOps, but also have custom workflows or proprietary workflows, you can certainly just do that as well. To try to also help you try to scale out, we also support our cloud, which is basically your own cloud solution using bare metal servers, and we basically allow you to basically use Terraform for that. So the impact of AI is clear, and it's transformative. These are graphs of the contributions using generative AI, and we basically use the generated by tag, and this is why I've been a big advocate of using this tag in other projects. That way we can scale out and see the impact of generative AI on open source projects. But I'm also here to talk about, in particular, that how it can actually be more transformative. So let's get into some of these things. So part of the tricks basically is let's evaluate how you make testing file systems easier. You basically just use kconfig. Typically, people use scripts. Scripts don't scale. Kconfig has a lot of value. Well, why? Well, because LLMs today in C coding, they actually are pretty terrible. For English, it's pretty good. For kconfig, it's actually really great. So kconfig forces documentation and enhances determinism and enhances automation as well. We have also plans to integrate kconfig SAT solver integration. There's patches out there that we're collaborating with the university for that. And essentially, the target here is basically to allow you to describe your target requirements, and basically kconfig basically just provides full resolution for you. So the lesson here is that the less code or makefiles you have, the better. We also have support for dynamic kconfig, which a clear example for that is basically you don't want to keep adding tags for Linux's releases and stable releases of the kernel or Linux Next tags. That's a clear example of where you want to generate kconfig dynamically. Another more complex example is if you want to do parsing of a PCI table to basically support PCI pass-through. A while ago, we theorized that basically maybe we can also leverage this to also scrape cloud solutions and basically get all the instances that a cloud provider supports. Well, generative AI proves that this can be done. We have support for this first with Lambda Labs as a Neo Cloud provider, and then Chuck basically recently added support for that with AWS as well, and he's working on Azure support now. So KDevOps adaptations are easier. What I mean by that is basically you want to write out your code first manually, and then you automate afterwards. Clear example of this is the work that we did for Sysbench and testing Sysbench for the work that we've been doing to evaluate large atomics on MySQL and PostgreSQL. An example of this is basically just a simple Git repo that has a series of scripts, and then basically ask the LLM to try to, port this into KDevOps. Back then in 2024, I gave it a rating of D-. However, generative AI is getting better, and for plots it was really great, but now generative AI has gotten much better, so we basically tried the same thing again. In this case, we basically did this for porting Milva's series of scripts into KDevOps, and basically it did pretty good. So just keep in mind that's going to get better. If you're not sure how to prompt onto KDevOps, we have a series of prompts.md file examples that you can basically look at and see how we've actually embraced generative AI to enhance KDevOps. So therefore, KDevOps is a Linux software 3.0 enabler. And what do I mean by that? Well, for that, I like to quote Andrew Karpathy. He's an AI researcher, founding member of OpenAI, ex-Tesla AI lead. And he's coined the term software 1.0. It's basically his manually written code. We also have software 2.0, which is basically train neural networks to write code. He also coined the term software 3.0, which is basically programming carefully with English. He's also the person who has termed the vibe coding term, and that's basically loosely prompting and hope that it works. Obviously, clearly, that's not exactly what we want. So what we strive for is really just to carefully program in. One of my favorite tweets from him is basically how the hottest new programming language is English. I think that that's becoming true. So we basically just want to make automation a fundamental part of the architecture here. That's essentially what KDevOps has strived for. And so I'm here to say that singularity for testing is here. So what is the singularity? Well, it's a borrowed term from physics, where you basically just can't see beyond the event horizon. I can no longer predict clearly what we cannot do in KDevOps. Time estimates for project scoping is completely way off. In writing these slides, I couldn't keep track of all the new features added. And I'm having a hard time prioritizing innovations. And it's just not me. So has this been useful for something productive in Linux? Well, check this page out. This is basically the work that we've done to basically enable LBS on the Linux kernel. And the amount of testing that we put into that. It used to take many years to add a complex file system feature like that. And now we're basically able to do that within a few years. I remember a lot during LSFMM, it was like called out, oh, this is impossible, it's a lot of work. Well, we got it done. We also have KDevOps results archive. We basically need a home to archive as much data as possible for results. We need infinite storage. Is it possible? Yeah, just use git LFS and rotate git trees by epoch. That's it. So the latest dog tricks by KDevOps is basically, we've learned that CI is a pain point. Generalizing it would be amazing. And yes, you can partially vibe code it, but it's the nastiest part of automation. So the goal is avoiding having developers to touch it. And for that, I have to give credit to Daniel, who's going to talk about what we've done there.
Yeah, well, with CI, what we did was turning KDevOps into a CI accelerator. So something where you can just offload your testing infrastructure into this CI. In KDevOps, we support more than 100 profiles. It's closer to 200. I don't have time, but essentially what I want to discuss with people is like showing what are the profiles we support. We support block test, ext4, XFS. We support like hundreds of profiles. What a profile means is like a set of workflows that you will run, and you will specify a goal. For example, KDevOps will run these VMs and will describe those VMs will start executing your recipe, and we are enabling like some subsystems already, all of these profiles that I've mentioned. And the question in this for this is, who is willing to start getting spam and getting CI reports from KDevOps? I have started with block test. This is, and I don't have time for this, but basically the problems that CI currently have, we cannot scale. There are like some limitations on how you scale KDevOps and profiles that you want to run in a CI infrastructure, but that's more or less what we can do. But let's say we fix this, it's fixable. If you guys have experience with this, I'm happy to talk in the hallway. But yeah, let's say you are a log layer maintainer. Are you willing to get some reports? How are you gonna go and look at the dashboards, getting some emails, modules? Are you a modules maintainer? Yes. So I'm willing to get these reports in an automated fashion. We also have support for KPD. I mentioned it. I went over the slides, but that means that patches that are posted into the mailing list are automatically tested with KPD and KDevOps. So we have that integration. So the question is, we have ext4, XFS, and we have machines now for testing this stuff in a CI manner. We are currently testing every Monday latest Linux tag, and every day we test the latest Linux next tag. So we are able to provide these results already, and we can also, of course, integrate more profiles in KDevOps. It's just a matter of describing what you intend to do with generative AI and use the output of kconfig and the grammar of Ansible and get the workflow going into KDevOps.
Are you already reporting to something?
We are getting reports ourselves, but we are not sending these reports out there yet. And the question is how the community would be, or every subsystem would be able to, get these reports out. You can get the results archive and look at the infinite Git repo, that storage repo that Luis mentioned. But how is the way that subsystems are willing to get these reports? Is it like similar to what 0-day does today, or is there any other mechanism? I guess some maintainers may have some different preferences.
Can you open a discussion maybe on kernel CI of getting such data? And
I think we have some kernel CI integration, right, of KDevOps. I don't know if they are getting these reports integrated somehow. They can, I don't know.
Yeah, so have spoken to Gustavo about this, and integration with kernel CI is really just a simple integration thing. We just haven't done it yet, but basically we can complete that pipeline for sure.
Yeah, the question is, do you know if maintainers are currently looking into reports in a dashboard manner, or how do they ask these reports? In which form they are provided to them?
you did find some bugs by this? So I think someone. Oh. You found some bugs with it, so
yeah. For example, right now block test is failing, I think, since 6.15. But yeah, on the way we've changed a little bit the architecture, and I haven't been able to report it. I think it was announced some time ago in the mailing list, and they was interested in block test. I also talked with the MapleTree and XRA maintainers. I think from the MapleTree, at least, Luis, I think you talked with both of them. They were interested in. I'm not sure. It's not clear to me how they are willing to get these reports from, like which manner. I guess mainly list. It's a good way, but I don't want to start spamming anyone if they are not. Yeah, I want to have a.
But like you can like look the result and check which one is. Why sending so much?
Why
sending so much mail when the result is like you're not breaking every time? Or yes?
Oh, right now, if you, for example, have something broken, every Monday it will be tested on Linux tag. tag, and then if it's not fixed, then Linux Next testing would be run against this broken code, and then it will be sending reports all over and over.
So maybe it could be like some regression things, like if it's always breaking.
The same, then you
Yeah.
hold and you stop. That's what you mean? That detect that specific case is the same as the other, right?
Yes.
Okay. Yeah, definitely.
Or at least cleaning what we are showing to upstream.
Okay.
Any
So thanks for the great talk. So I'm Shinichiro Kawasaki from Western Digital. I'm the maintainer of the block tests. So actually, so very similar block test CI activity is ongoing now. And then it was discussed at the last LSF at the Montreal in January. And then so your question, especially for the block test and the storage maintenance, that was the discussion topic at the LSF. So can we start reporting the automated bug reports? So so in this room, I'm not sure how many of the block layer engineers are in. So maybe, so not the plumbers, but LSF will be the place to ask the question for the block test. So that is one comment. And then if you already finding kernel bugs, why not you don't report it?
Yeah. I thought it was somehow aware, but if not, I'm sorry for that. I'll take responsibility for it, but I'll send a report to you. I'm also very much involved in that. I believe it was because mainly right now it's the testing that I have enabled in the CI, and then I get these reports, right? And I'll let you know when it broke, but I think it's around 6.15, and I forgot what are the profiles that broke, but it was one of the ones that I have it here. One of these.
Not only the bugs found by CI, but of course some other engineers of course report the bugs. So as to these bugs, I can do. You can do the same. And then the one more comment is that so Red Hat does CKI, and CKI does run the block tests regularly, and then they do reporting. So they do some triage manually, but that's really useful. So I guess you can do the same. You can do the same contribution.
Yeah, we definitely use KDevOps for our testing. Like we use to meta patch to the KDevOps repo Linux kernel, and then you can automatically test it for block tests, XFS, Btrfs, whatever you are testing. Sometimes you may have a patch that is actually across the tree, and then you can get the CI being tested across, right, on your specific test. But of course, you want to have a baseline. If there's a broken test with the current mainline code, you normally want to know beforehand that it's not your code that broke it.
So another question is, so does this test run for the per patch or for the does this test run before the patch merged apply to the Linux block branch? So
I'm not sure if I understand.
His question is whether or not these are running on the patches that are posted, and the answer to that is it's up to the maintainers. So we have support for both. Right now, Danny has enabled testing on every Monday on Linus's releases, Linux Next. If you want tests to be run on patches posted, we have support for that, but it has to be up to the maintainer to say, hey, I want this,
Yeah, essentially it's enabled through KPD. You just have a daemon in one of your servers, and then you just get the patches from the mailing list directly injected into KPD, and then that would trigger the KDevOps CI.
As to the block layer, so that's a question to the Jens, and then maybe the keys for the NVMe part.
Yeah, essentially that would require the maintainers themselves to say, hey, I want patchwork. And then for this to then start being the runners for the patchwork instances. And fortunately, Meta already did this work, and we've been collaborating with them on trying to enhance that. There's also lay-based patchwork instances in case your subsystem is really small and it's not part of a dedicated mailing list, but instead, let's say it's a single file that you care for and you want a patchwork instance for that specific small little file that you care for.
Thank you. So I think we are out of time.
Yep. Thank you.
Thank you so much. So is hello everyone, I'm Harisu Tachibana. I'm the creator and main maintainer of KCDev. So, okay, we are already late, so I will go a bit more fast. So I think this talk is probably for anyone that is interested in current testing and trying to make it easy by KCDev tool. So we have a massive combination of tree, massive data on kernel CI, and the dashboard is not just flexible enough for checking every data or filtering into all the data that we have. Like using dashboard for, like we have immense amount of data currently. And just for give a scale, we did like thousands of kernel build in last few days, actually 7,000. And practically kernel CI is checking upstream kernel and doing thousands of build. So we need a ergonomic way to filter this data and trying to understand, to have a easy way to see what is wrong and what we can do for make it better. So with KCDev, you can, of course, query in the result. You can filter in the result, filter by hardware, by there is many parameters that you can filter about. And you can also trigger tests. So now you can not just you in the test, but you can also doing like starting test on your own tree or your own branch and send such a test to kernel CI, and kernel CI have a distributed system for off laboratory. So I don't remember how many boards we have currently, but we have many. I don't, maybe more than 100. More than 100 boards we have on kernel CI. So you can start a test on your tree on these, all these more than 100 boards and get the result. And is also scriptable, is giving JSON output a table. Recently we have also graphic, and we have some real world context, like we have some developer with, at least as Gentoo kernel maintainer, I'm sometimes, I would like to use it, but currently is not yet implemented the Gentoo branch into kernel CI, but is something that I'm trying to do. We are using it for CIP, at least for every time that we have also our system on CIP, but we are starting to use also kernel CI, and this is giving the possibility to trigger a test on the CIP branch for commit on the CIP branch. And we have Chromium OS as that. Well, I recently got a pull request for adding Chromium OS coverage. There is already coverage in kernel CI, but KCDev can now make some kind of graphics for Chromium OS coverage, and then yeah, we have also some Gentoo kernel, but I talked before. We have also some. I don't, Mark, if Mark is using it. sometime. And so we have some real case or example of people that is using KCDev. So this is example how is like you give the tree that is already in KernelCI with some parameter, and you can do filtering by like, I want just this board to run, and it will run the test on this board. So what is needed? We are trying to get more maintainer using KCDev. And we are trying to trying to understand which feature we are missing on KCDev. And I recently discovered that we don't have documentation about bisection. We can do bisection with KCDev, like it's a simple script for doing bisection. And yeah, we have performance concern with dashboard, and this is something that I'm working on. So what we have some technical dev about we need to clean up the duplicate code, improve task coverage, robustness, and I'm currently working like to making in a way that it can be used also as a library. And I think so. What I'm working now with KCDev is I'm trying to make it some kind of library so that you can not only use by your command line by client, but can be also called by some, like there is patchwork that is trying to have make working KernelCI testing some like Mbox, getting the Mbox and testing it. And if KCDev can support such things as a library, I thought it was a good idea. So I start to send some pull requests for making it a library. And another things that we have is that sometimes KernelCI API change, and we need to follow such change. I discovered a few years ago that they changed something, and KCDev was not working anymore. So how the question that I thought was like, how we can make KCDev more usable for people that are maintaining kernel tree. Like not only upstream, but also like development kernel or distribution kernel. So yeah, I think I'm out of time. So if there is any idea or question of how KCDev can be helpful for it.
So does kernel CI support arbitrary test injection?
Okay.
That'd be kind of nice to be able to.
Is currently arbitrary. Currently not, but practically there is a way of having the current KernelCI pipeline supporting injection of something, and this can be like I think like a patch, and so KCDev could support such things by putting your patch somewhere, and that can be, I don't know, the KernelCI storage, and it will inject such things into the testing that it's doing.
Okay, so theoretically, could you, I don't know, I assume there's a kernel CI k-self test run. So if you did a patch that added a new k-self test, you could test that.
You can, oh, Apache adding new case self-test. I have no, like, yeah.
If you add a new case self-test into an existing self-test suite, then it will run. It picks which case self-test suites to run, not which individual tests. So, depending what you mean by a new case self-test, yes or no. Since I've got the mic anyway, you asked if patch series testing would be helpful. Yes, absolutely. I do that all the time. That would be fantastic. Currently, I personally do that with Git range, but Git ranges, but mboxes I'm sure would be useful for others. And I'm mainly using Git ranges because I'm taking mboxes and turning them into Git ranges. So.
So something that would be nice to have. Like some feature that could be interested to have in KCDev. Like something that, or in KNCI and that KCDev can call. Or like Chrome OS added the coverage testing. And as I say, there is some real usage currently of KCDev. So anyway, give it a try if you have time. And you can just install by pip install KCDev. I did the presentation few days ago, and practically everything that like the result filtering part, checking result of KNCI, and like playing with KNCI result can be done without any authentication. So you can just install that one and do all the filtering of KNCI data. The only things that you cannot send the triggering of new kernel testing. For doing that, you need authentication token, and you can ask to the GitHub of KCDev. Yeah, so that's everything from me, I think. Yeah. We have 20 minutes and okay, thank you. So next is Mark. Okay. Yeah, it is better to. What's the name?
If Eric's, should we get Eric's?
Hmm?
If Eric's available.
I don't see the name, so is Erin Karanja? Okay.
Yeah, so maybe do his talk.
Okay.
Before.
So Eric, can you share your screen and maybe share your presentation? Give. I made you a presenter, Eric. So if you can talk. Eric, are you in the room with us? Someone is being shared. So yeah, but we cannot hear you, Eric. So if you should enter as presenter, like you should share your microphone at least. I think you got with the Eric. We cannot hear you. Eric. Eric, can you unmute your microphone? Eric? Eric, can you unmute your microphone? Can you unmute your microphone? Ah, it's trying, but we cannot hear it. Yeah, you unmute your microphone and maybe, and what? I don't understand what it is doing. Hello? Yes, sorry. Maybe it's better if you and Eric can figure out what is not going well. So, what was the presentation name? Okay.
There we go. I'll just... Hopefully Eric can rejoin later. I was going to say to thank you all for staying for the last presentation, but maybe it won't be. Hi, I'm Mark Brown. I'm on the kernel team ARM. One of the things I work on is testing, and one of the things we've been working on recently is benchmarking. So I wanted to have a bit of chat about that and get some feedback about what we've been doing, and get some ideas for things we could do that would be useful for the community. So I'm going to start off by briefly going over what we mean by benchmarking. Then the bulk of the presentation that I have is about tooling for the structure we put around benchmarking, how we think about them in general. This is based on a tool we've been working on internally and have recently released publicly called FastPath. I have one bit about that to introduce it to you. And then finally, if we get to the end of the presentation, I've got a slide with a list of interesting benchmarks. We can maybe have a chat about what benchmarks are interesting for people. So the general goal with the presentation here is that it's supposed to be a prompt for discussion and ideas. So please don't wait for the end. If you've got questions or comments or anything like that, jump in as we go. And if we run out of time, then that's fantastic. And will the slide transitions work? Yes, they will. Wonderful. Most of the testing we've been talking about today has focused on functional testing, simple, straightforward tests that are very easy to run, as we've discussed, which either pass or fail. But that's not suitable for everything, especially things associated with performance, but not exclusively those. And for those, one of the common cases is that we want to track how numbers change. So either one number by itself or a group of numbers. We want to track to see if the number's changing at all. We need to be confident about how accurate the number we have is. Does that make sense to people? People are either nodding or nodding off.
Yes.
Thank you, Tim. Yeah. So this has all the complexities that we have with regular testing of pass or fail results, but it's got a bunch more. There's an issue with figuring out if the test you're running to verify the performance of something is actually representative of the performance of something you care about, or this is particularly common with things like micro benchmarks, where you're zeroing in on some very small aspect of performance, but maybe that's just a tiny proportion of what happens at runtime and nobody really cares. You also have issues with finding tests that actually show changes when something that users observe is impacted. That's the other side of that. There can be issues with getting the test to run twice and give a similar result. Some of the benchmarking requires huge amounts of resources, or it's difficult to set up. And finally, if you're running a full system test of some kind, it can be really, really hard to work out exactly what has happened when the benchmark changes. That, again, does this make sense to people? Any other issues with benchmarking that I have neglected to mention?
Well,
Aaron?
on the subject of generality, right, the hallmark of benchmarking is that it's system dependent, right? So there's hardware dependencies. I don't know if you called those out specifically, but
yeah. And there's a related aspect to that is that to what extent is the performance or change you're seeing with a benchmark something that happens because of the specifics of that system, or to what extent is it a general thing where any system running these tests would slow down or speed up depending on how good things are getting? Darren, you had? Yeah.
One of the things I've been running into working with our performance team has been, we get a change in, my team runs a test, results are terrible, right? We're like, okay,
they're great.
You guys need to go. You guys need to go like look at this really carefully. And then performance team comes back, and they configure the system differently because their goal is actually to showcase the hardware in the best way possible. And so what that highlights is maybe configuration is up here. Maybe that's part of complexity. But I think trying to understand what are we trying to accomplish with that benchmark? Are we trying to get the best result in the benchmark? Are we trying to get the worst result with that benchmark? And and which one of those matters and why that one's tricky.
Yeah. Yeah, and different audiences will have different requirements there, benchmarking our own stuff, we want to get the big number. Benchmark competitor stuff, we want the little number, or vice versa, depending on the direction of the benchmark. Anything else on this? Yeah, let's skip on. So I mentioned FastPath at the top. Oh, sorry, Tim had a...
When benchmarking, kind of on the same thing, when you're benchmarking, right, all the like to detect a regression, you have to compare one number to another, right?
Yep.
So, and the problem, since you have all these other complexities involved, is that my set of numbers, my thresholds for what constitutes a regression are going to be different than everybody else's thresholds for what constitutes a regression. And it creates a real problem for sharing test results, right?
Yep.
And so that is like a really, really difficult issue to solve.
Yeah, I've got a slide about that, about statistics, which is essentially the thing. But yeah, that's definitely a big problem. Is
yeah, I think one point I'd add, ironically, increasing the scope is scope. So, from our perspective as GPU people, we do as much as we can to isolate things like scheduling, PM, etc., and filter those out into the domain of not our problem, so we can figure out if we've screwed up. As people who also want to ship products, it's interesting to know the global behavior. But I think I think it's an important consideration of like, are you trying to figure out if you yourself have gone backwards, or are you trying to figure out if the kernel more generally has gone backwards in some way, or forwards?
Yeah.
Sometimes it goes forwards.
Yeah. No. Yeah. Application versus system versus micro benchmarking is. Yeah. It's a. And there's not an answer to that. It's depending on what you're doing on any given day, and you probably want to do all of these things. More comment, more feedback on this, or? Okay, so back to talking about FastPath. This is the one advertising slide I have in here. I'm not transferring to the marketing department just yet. But a lot of the work we've been doing that I mentioned up top is about centered around this tool called FastPath, which, like I say, we've released recently. It's a command line tool which can run benchmarks both interactively, and it's also intended to be hooked into CI systems. It can manage a store of results, and it provides some UI for looking at the results. I've got a bunch of examples of these things to prompt discussions about them later on. All the examples I've got here are drawn from FastPath, but they are static examples. I'm not going to do a demo. I'm not a fool. So as I mentioned, this is open source software. We released it earlier this year. The URL for the documentation, which links to the actual code, is on the slide there. And I've been saying that we've been doing things. That's a bit of a lie. I'm just a user of this stuff. The actual work has been done by other people who unfortunately couldn't make it here today. So the main team on this is Ryan Roberts, Aishwarya Rambahandran, and Aishwarya TCV. But please do check out FastPath. We'd love to hear from you if it's useful, if it's not useful, whatever. So one of the issues that we ran into when we were looking at this that sort of fits in the complexity thing I was mentioning before is the execution environment. Micro benchmarks, it's not such a big deal usually, but for once you get into system application level and especially system level benchmarks, you tend to pull in an entire OS as your software stack, which if you're running on diverse hardware, making system images for the diverse hardware is not necessarily a fun use of time. So the way we've tried to solve this is that we treat, we have a base OS image on all the hardware we're testing on. We treat that as being part of the system description. It just sits there. It does as little as possible, and it runs Docker. And then we pull in the image with the system image with the test in it as a Docker container, and FastPath drives that. So I don't know if anybody else has any bright ideas for how to deal with this, or sees any obvious flaws in what we're doing here. I'm going to take that response as universal acclaim for our brilliant design and move on. So having run the tests, we get onto the thing Tim was mentioning about trying to work out if we trust the results and if we think the results are telling us anything. Fortunately, this is not an unusual problem. There's a whole field of mathematics devoted to trying to solve this problem called statistics. So yeah, you run the test a bunch of times. You might have run some warm-up runs first if you're worried about caching effects. And then you smoosh all the numbers together into some summary numbers, which you hope tell you something. So I've listed a bunch of them on the slide there. You know, you take the average, use that. You look at how stable the result is, minimum, maximum standard deviation, so on, and confidence intervals around that. Darren is.
So with respect to statistics and populations, standard deviation is a property of a normal distribution.
Yeah.
So I guess you're obviously giving us a summary. Do we characterize the distribution and then use relevant statistics for them, or is standard deviation included in everything? So if you're talking about things like latency is usually a Gaussian.
Yeah.
And so we'd want to use a different.
Yeah.
Okay.
Yeah. No, this is a list of numbers that we might care about. Here are some. The stuff we've been doing has we've not particularly needed to put. It's been these sort of things that have been appropriate, but yeah, the idea was to trigger a discussion here, not to say this is everything. I should have mentioned before that the good ideas here come from the team I mentioned. I've put some obvious errors in here to troll you all into discussing. Julia.
You produce some kinds of nice graphs or pictures or something like that to show like
yes.
and, bad results. And so on.
There are some examples later to trigger a discussion about how we want to look at things in pictures. Tim.
So I don't know if it goes on this slide or some other slide, but again, if you're converting this into an actual test result, like was this slow enough to warrant human attention or fast enough or whatever, then usually you end up with a hard threshold.
Yep.
And then, right, so you use these to determine, right, the hard threshold's not going to be like the last value you saw, am I faster or slower than that? It's that plus some standard of deviation or...
Yeah, or like one thing we've there is something about this later, but maybe we'll just talk about just now. One thing we do is use the confidence intervals there. So if we've got a change that's big enough to show non-overlapping confidence intervals, then you can use that as a to give you to detect if you've got a real variation or just a random change. Although, of course, then you might miss the gradual changes if you don't pick your baseline
just
well.
One more thing on that, right? So if you're trying to generalize this, which I've tried to do in the past, then sometimes you're comparing if a number is higher, or sometimes you're comparing if it's lower. And so you actually, as part of your comparison operation, you need to know the direction of the threshold.
Or you just don't. You're just looking for a change, and you investigate both. Okay. So
how do you store the test results persistently?
I didn't actually put anything in the deck about that, but put them in a database. I don't know.
That's actually a great segue to the question I had, which was, it sounds like you were describing these like a confidence interval, for example, as summary numbers that are being produced. But if it was stored in a database, it would be really convenient to be able to query and be able to calculate these dynamically. Is that what it does already?
Yeah. So we store the results in the database, in the database, and then statisticize it later.
So, but that goes back to Tim's point about people having different criteria. So that would be really useful.
Yeah, but and you can go and then slice and dice in whatever way you find amusing later on. It was.
I think interesting segue as well to what you said sort of early doors about how do you trust not just the results from within the run, but how do you trust the results over time? And it sort of occurs to me it's a similar problem to binary tests, right? In which one thing I think would be really interesting from this is to take an aggregate of aggregates. So, issuing the same job over and over for SOAP testing, and for binary testing, you can say, okay, same build, same device, this test is flaky as hell. And similarly for non-binary results, you could sort of extrapolate, okay, over time, this is the noise in the trend. So, you at least know what a meaningful deviation from that looks like, if that makes sense.
Yes, similar thing. And I see we've got a question about how the database is stored. So for FastPath, it can be local, it can be remote. It's intended to support plugging on the back end. But we currently have local or remote as options.
Have you considered using change point detection?
I do not know what that is. It's possible the people working on it do and have considered it, but I don't. Could you tell me, please?
It's some kind of statistic that allows you to realize when the thing that you're observing is different than what you observed.
Right.
Significant way. So you don't have to have a threshold for.
Right. Okay. So that's kind of like the idea we were talking about using. I was talking about where it uses the confidence intervals to say is the number actually different or not. You might also want a threshold though, depending on how good your confidence interval is. If your confidence interval is too good, you might detect noise anyway. So that's change values. Change points, sorry. Yes. Okay. I will. Like I say, I'm not the guy working on this, so. Arsu, did you have a question or? Oh, sorry, you were holding the mic. Anything else on statistical properties? Okay. So, yeah. You've run your test, you've got your results, you've computed some statistics. You might want to look at them. One way you can look at them is with, you can write the numbers in a table and read the table. Here are some tables with I think the top one is a fairly raw display of numbers from a given run. The bottom one is an example of taking a baseline and doing a comparison to show changes, see if something's got better or worse. This is Ryan had implemented some optimizations to huge pages stuff, and apparently they were doing something useful. Any thoughts on what ways it's useful to look at things, or is this it? Or if Jeremy's got a, I don't know where.
So the bottom table, interpreting that, so you've given a label to a different set of input data. Is that right?
Yep.
Right. With and without.
Yeah. So you've got run without THP and run with MTHP and or run set, I should say. A collection of runs. But not everybody wants to read numbers. You might want to look at some pictures instead. So this is one example of a graph or a graphical representation. I think it's actually the same test runs we're looking at on the previous slide. So you can see that there was a before and after, and there was a big change there. These results plot the I've got 5 minutes according to my watch. These are plotting averages, and we also have the minimum and maxima. I think there's more things swooshed in there, but you can basically only see the minimum and maxima. So it gives you an idea that the first run on the left-hand side there was not very stable, and but the rest of them were a lot more stable. There was some changes going into the, but not very big ones. And then the optimization was implemented, and then we had a nice big change. You can also look at the same thing with just a simple graph showing the deltas. That's much easier to glance at, maybe. but it doesn't show you things like the confidence interval on the first result. So maybe that's you're missing some information there, and you're it's not giving you a glanceable view that there's a lot of noise. And then we've got similar plots. This is something that's a bit more over the place, doing the same graphs. And there's an inconclusive benchmark, which is sort of jumping about all over the place. These graphs seem useful to people. Are there other forms of graph that people wish they could see? Histograms. Yep.
Just depending on your type of test, a histogram might be appropriate. Right?
I've seen some rather lovely for real-time 3D graphs with a distribution plotted on the x-axis, then extending it into space through time.
So this is not about the graphs, but some data you might want to store. It's nice to keep some metadata around about the system under test.
Yes, that is. So we we fingerprint the systems when we and then we record which system we ran the we ran each run on. So yeah, that's something FastPath. I sort of covered that in the execution. Or this was intended to not really be a FastPath marketing thing. It was intended to be a benchmark ideas solicitation thing that happened to market FastPath. So I didn't go into that details of how FastPath does it, but yeah, it does do that. Okay. And then, yeah, this is the last slide before the list of benchmarks. So we're probably not going to get the list of benchmarks, maybe, but yeah, looking at the results by hand is all well and good, but that's well, that takes time and effort. And why would you do that when you can have the computer do it? Making a pass-fail or making a number in benchmark result into pass-fail is useful. We've been doing that, like I mentioned before, by looking at the confidence intervals. The other fun thing we've done, which we found useful, was that if you're doing a bisection or something and you don't necessarily intend to look at the intermediate results long term, we constrain the number of runs we're doing by looking at the confidence intervals and just stopping doing iterations whenever we decide that the confidence intervals are non-overlapping, which saves us a bunch of time with the more expensive benchmarking. Arasu is looking threatening at me with the microphone, so I am almost out of time. So,
yeah.
Does anybody have any final thoughts before I give up? Or do we all want to go home? And
Yeah, because Julia wanted to do some part of.
I'll just say that the great thing about if you can pull this off, benchmarking, there's almost nothing you can't turn into a number.
Yeah.
and benchmarking, if you have a generic way of turning a number into a pass-fail, then you've got yourself a neat test.
Cool. Okay, and then Julia. That really is just a random list of benchmarks intended to make people think of things. It wasn't. It's not intended to be comprehensive or anything.
Yeah. So one quick thing which I've been struggling with in terms of figuring out how to do benchmarking is I make fairly extensive use of cloud VMs where once I'm done running the benchmark, I want to be able to shut down the VM. And then when I bring it back up, it's very likely going to have a very, very different system fingerprint. And so there are two problems. One is, the whole fingerprinting story where I want to know about the VM, and then the other part is persistence. So I just want to register that. We probably don't have time to chat about it.
No.
we don't.
Thank.
But yeah, come and find me later, or like I say, go to the FastPath website and talk to us. Thanks for your attention.
So next is Julia. So, if you can wait. Sorry if we are a bit out of time. So
Okay, so this is the work, almost entirely the work of Eric Muthama, also known as Eric Karanja. He was my outreach intern this summer. So the goal of this project, here we can see, is automating scope-based resource cleanup with Coccinelle. So the sort of the goal idea of this project was we have Scope Guard and we have Guard, and they can make your code simpler. But on the other hand, they can also be introduced in an incorrect way. There's various ways in which they can be incorrect. So the goal of the project was to try as hard as possible, at least, to make something that would only make the transformations in the very safe-looking cases. And to give the very short overview of the talk, because I know we're very close to the end, the semantic patch is not part of the kernel. We have put it on GitHub because we don't want maybe everyone in the world to feel like they must transform their code to use Scope Guard. He got some pushback when he tried to submit some patches. Some people appreciated it, some people didn't appreciate it. So the idea is, if you would like to see how Scope Guard might help your code, then you can use his semantic patch and see what's going on, and perhaps avoid some common pitfalls. So basically, the idea, if you're not familiar with it, Scope Guard is helping you with things like lock and unlock. So lock and unlock, mutex lock, spin lock, whatever. These are just things that go by sequence in your code. There's no scope that's associated with them. I have a colleague who's very fond of like jumping from the beginning to the end of things. With Scope Guard, you get nice braces. You can see exactly where your critical section is. You also don't have the unlock. You just have a line for the locking aspect. And there's also the issue of the go-tos in between. So you don't have all those unlocks along the way in your air handling code. So that is often, historically, they have often been forgotten in some cases, which could lead to some deadlocks and so on. So there's two options. One of them is guard, and guard is when you want to take a lock at some point and keep it all the way until the end of the function. So here's an extremely simple example. Here we have guard. It's actually, this is just a two-line function. So we have guard. We take our spin lock, IRQ save, and then the second argument, it takes two arguments. The first one is the lock that you're related to the lock that you're interested in. The second one is any other arguments that are necessary. And then this lock is going to be held until the end of the function. It will be released implicitly when the function is departed. And then Scope Guard does the same thing, but you get the braces that is for the critical section. So here we have an example, Scope Guard. another spin lock RQ save, and this time we have 2 statements in there, and those are the things in the critical section, and then we go on. So these are very simple cases. So it reduces code clutter, the code is safer, and the intent is more clear, it's more obvious exactly what the region that is intended to be stored is intended to be protected by the lock. So here, I believe, is a example that illustrates why all of this is interesting. Here we have a mutex lock at the top, and we have a mutex unlock at the bottom. But here you can see we have a return, which is going to jump out of the function. And we ought to have a mutex unlock there, but there is not one. So if we transform this to use scope guard, then we will have a scope guard at the top. We will have extra brace at the bottom. And this part in the middle will be exactly the same. We don't have to write the unlock explicitly. The return will cause the unlock to happen. So this is kind of the basic outline of the semantic patch that is going to do this work for you. So basically, you see up here at the top, we have a call to a lock. So this is parameterizable according to what lock you want to use. There's, at the moment, I think there are maybe 50 different kinds of locks that are being using these features in the kernel. So you definitely don't want to have to write a separate rule for each one by hand. So it's parameterizable on the command line, and the GitHub repository has a make file that you can use to configure to do whatever kind of lock you're interested in. So when we have our lock, then we remove that and we replace it by scope guard. When we have our unlock, it might be a little bit surprising, but we remove the unlock and we replace it by a close brace. And in the various cases in the middle where we have unlock that's followed directly by some kind of jumping thing, then we remove the unlock. And so the thing is done in 2 phases. First, everything is transformed into scope guard. And then in the special cases where the scope extends from some place all the way to the end of the function, then it gets transformed into guard. So that's kind of the high-level overview of what it does. As I mentioned, the script is available on GitHub, and you have the link here, which you can find on the slides that are in the on the internet. So basically the semantic patch is in several sections. First, there's a lot of analysis of the code to find cases that we don't like. And all of those cases that we don't like, the positions of those locking functions are recorded, and then the actual transformation phase doesn't do any transformation at those positions. So we protect against a lot of possible pitfalls. Skip that. So here, for example, sometimes what people do is they take a lock, and then inside a if they may do an unlock and then another lock. There's no way to transform that into scoped guard because the braces come out. There's no nice scope that reflects the critical section because it just doesn't follow the scoping strategy. And so no transformation will happen in this case. Another issue is that scope guard hides a break. And so if the space between the lock and unlock has a break, it detects that and no transformation will happen. This is just a real example of that. Another case, let's see what this one is. Unlock at else. I believe it's because I don't want to spend time on this because I don't really remember the details here. This is another case. This is an important case. Here we have an unlock. I'm sorry, this did not come out very well. These were PowerPoint, and then they get translated with LibreOffice to PDF. Here we have a lock. And this looks kind of like our correct case. We have our lock at the top. We have our unlock at the bottom. We have an if in the middle that is doing a return. But the unlock is followed by some function call. And if we transform all of this into scoped guard, and we remove this unlock, then the unlock will implicitly move down to the point of the return. And that might be safe or it might not. And since we don't know, we don't do that anything in this case either. So here's an example. And another case is also when you have a go-to, you can have a similar issue. Here we have go-to label. At the label, we have some unknown function call, and then we have the unlock. If we had transformed this to use scope guard, then the unlock would move upwards this time to the to the boundaries of the scope. And so then our function call, which was supposed to be with the lock held, would not have the lock held anymore because the lock would not be held at the go-to destination anymore because that's outside the scope. And so then if we protect against all of those different situations, then we can do some transformations that you can see here. Another example of a transformation. To check for correctness, at the moment we just do compilation. Incorrect things tend to kind of break the scoping boundaries and so on. And then studying the diff in general, when you use coccinelle, you have a responsibility to check manually that what the tool has done for you is actually the right thing. And this is just a count of remaining opportunities. You can see that is a lot of work left to do. If we want to transform them all, we're not advocating that we need to transform them all, however. It's just up to people. So I think we're out of time. I see a stop sign there. But if you have any questions, you can contact, especially Eric. It's very unfortunate that he wasn't able to come, and even more unfortunate he could not give the presentation, but he did an enormous amount of work on this project and really excellent in understanding all the possible problems and so on. So thank you very much. Thanks for the time.
Hello. Okay, so I think we are at the end. Thank you everyone for coming. Thank you, Xuan, Sasha, Guillermo. Without them, this would have been possible. So thank you everyone. Thank you, and have a nice day. weekend. Yeah.